So good morning and welcome to the next in the series highlighting organic chemistry. And this year, as we travel across Europe, we're very pleased to have highlighting organic chemistry in the United Kingdom. So my name is Pat Gowrie. I'm the president of the Division of Organic Chemistry for EuChemS. And it is my pleasure now to introduce Dr. Will Ullensworth, the UK representative on our division, who will tell us a little bit about organic chemistry in the UK and then introduce our first speaker. So Will, over to you.
Thank you, Pat. Right, so I'm just going to share my screen. I think you should all be able to see that now.
All good.
So, thanks, Pat. So, as Pat mentioned, I'm representing the RSC today. So I'm on the European Chemical Society Committee, but I'm also on the Organic Chemistry Community Council, which is part of the RSC, which many of you, I am sure, will have heard of. On this slide, you can just see the kind of broad goals of the Royal Society of Chemistry that will presumably echo the goals of many of the chemical societies that all the different participants from around Europe really are members of. So dissemination of knowledge. Certainly, many of you will be familiar with the journals that the OSC publishes, Chemical Science, ChemCom, LBC, and many more. Advancing qualification standards, serving public interest, and this last sentence really sums things up. Advancement, of the science or practice of chemistry. So that's what the RSC is all about. And one thing that perhaps sets the RSC apart a little bit is how old we are. So the RSC is now over 175 years old and is the oldest chemical society in the world. I'm reliably informed. Just to get a sense of that, the first royal charter of the RSC was granted by, at the time, a quite young Queen Victoria. So we really have been around a long time, and chemistry and organic chemistry has changed an enormous amount in that time. I'm sure we can all agree. In terms of the structure of the RSC, it has different subject community councils and interest groups. And in terms of the organic community, we're led by Professor David O'Hagan, the current president, and we have a committee of around 15 or so members of the council from industry and academia. The three people here, so myself, Louis Morrill, and Joël Prunet, were tasked with selecting 7 speakers to represent UK organic chemistry today. And really, this word comes from the website describing what our group's about. And the highlighted section, really, organic chemistry in its broadest interpretation. This other section, all areas of organic chemistry. The three of us really wanted to keep these definitions in mind when selecting the speakers, which I'll say a little bit more about later. So I was asked to say a little bit about the UK. So here's a big Union Jack. One thing I'll say today, we have speakers representing 3 of the 4 nations that make up the UK. So we have speakers from England, Scotland, and Wales. We don't have a speaker from Northern Ireland today, but before any Northern Irish participants shut down this meeting in protest, I'll just point out that Northern Ireland were represented at a previous incarnation at this event, together with Republic. The RSC itself is representing all 4 nations within the UK and the Republic. So, and certainly the UK has a strong and long track record of chemical industry, particularly pharmaceutical industry. I would say historically we've had representation from all the big pharmaceutical companies. Within the UK, that representation has dropped a little bit in recent years, although we still have big sites from AstraZeneca, GSK, and Syngenta. There's a big agrochemical presence, but even as perhaps big pharma has dropped a little within the UK, the number of smaller companies or SMEs, biotechs, and contract research organizations seems to continually rise. And I would honestly say that the the job market for organic chemistry PhD students at the moment in the UK is as strong as I have ever seen. And speaking especially to our European friends today, I suppose recent political decisions within the UK, and I refer specifically to our decision to leave the European Union, may make the UK a less attractive destination, but please be reassured that certainly the scientific community, both industrial and academic, is very open, very welcoming to our international friends. And certainly in my experience, acquiring visas to come and work in the UK for PhD level scientists is rarely a problem. You can find all sorts of statistics about the importance of chemistry, like this one I show here, where you see very big numbers of money indicating how important chemistry and organic chemistry is to our economy. I must admit, I find these kind of numbers a little bit hard to digest, and I really prefer to think about the impact of what we do. And this is something we perhaps do not enough when we're working on a project in a very specific area and can get bogged down. But this graphic is produced for chemistry, not specifically organic chemistry, but pretty much all of these applications do rely on organic chemistry to a larger or lesser degree. And I think it's important to hang on to this fact that what we do as organic chemists is very important. In terms of academic chemistry, the UK certainly has an extremely rich history. Here are 3 black and white photographs. I've deliberately not captioned them, so you can you've got a few seconds to lock your answers in if you want to have a little quiz amongst yourselves about who these 3 gentlemen are. So over on the left here we have Perkin. So this is Sir William Perkin. In the middle we have Sir Robert Robinson, and this is Sir Derek Barton. So all giants really of organic synthesis, and 2 Nobel Prize winners here in terms of Robinson and Barton. And the history of UK organic chemists winning the Nobel Prize continues. So we have here is Sir Fraser Stoddart and Sir David Millen, so 2 scientists born and educated in Scotland, and although they've gone on to participate in their careers outside of the UK, they've certainly expanded on this legacy. Within the UK, there are around 55 is the number I came up with, universities that offer a chemistry degree. 60,000 students each year set a chemistry A level, which is the pre-university qualification. And I actually struggled to come up with these numbers, so I've been a little bit cagey. But I'm saying around 15,000 undergraduate chemistry students and around 5,000 graduate students, predominantly PhD students doing chemistry. The reason I'm so cagey is that it's actually very difficult to decide who to count. So I've been thinking a lot more about what an organic chemist is, who do we count? Because these numbers are encompassing degrees with chemistry as the first word. But what about biochemistry? So I think it's reasonable to say that any good student of biochemistry needs a strong ground in organic chemistry. And if we're going to go biochemistry, what about material science, chemical engineering, pharmacy, medicine, you name it. There's all these different scientific fields need organic chemistry. We are important, and so I've come up with this slightly grand statement. Number of organic chemists outweighs the number of chemistry students. So we are really at the centre of a lot of this. And just to hark back to Nobel Prizes, so this is the 2022 Nobel Prize. So we have 2, in terms of Mendel and Sharpless, what I would say are card-carrying organic chemists over on the right. But in terms of Professor Bertozzi, who really drove the bio-orthogonal chemistry part here. Of course, Professor Bertozzi has a chemistry undergraduate degree, a PhD in classical carbohydrate synthesis, so another classically trained organic chemist. So just to preview what we have coming up today, as I said, we wanted to keep this flavour of organic chemistry in its broadest sense when selecting the speakers today, and I hope we've been able to achieve that. So we're going to kick off with Professor Steve Goldup from the University of Birmingham. So Steve is someone who did a PhD in total synthesis, but has gone on to do all sorts of beautiful and creative chemistry in the realm of mechanically interlocked molecules, which we'll hear about very shortly. We can go on to Amanda Jarvis, who's going to talk to us about metalloproteins, so kind of organic chemistry tying together the biological and organometallic type areas. Stephen Clark is best known for his beautiful work on natural product synthesis. We then move on to our Welsh representative today, Professor Rebecca Meelan, who will be talking about frustrated Lewis Hers, so bringing in main group chemistry. Duncan Brown is going to be telling us about mechanochemistry, so bringing in elements of chemical engineering. Ailan Lee will tell us about some exciting modern radical chemistry, and we'll finish with Ed Tate, who will be telling us about chemical biology and protein modification. So again, showing organic chemistry has the ability to impact these important areas: medicinal chemistry and pharmaceutical science. So just return to this slide now. We have this caption: chemistry is the central science, touches all aspects of our lives. I'm sure you've all heard this phrase before about chemistry being the central science. I'd actually take it a little bit further and say that if chemistry is the central science, then organic chemistry is the central chemistry. And I hope we can kind of keep that thought with us today when we hear from the 7 fantastic speakers we have lined up. So that is absolutely enough from me. So I will stop sharing this screen. And brilliant, we have Professor Goldup with us. So Steve, are you able to share your screen, please? Brilliant, so that's working fantastically. In these types of meetings, in my experience, the schedule can overrun and technical hitches can come up. So I've made the decision to keep my introductions extremely brief. Okay, this is no disrespect to the speakers, but frankly, I think we all want to hear from the speakers much more than we want to hear from myself. So I'm just going to introduce each speaker by name and institution and hand over to them. So without further ado, let's kick off the meeting with Professor Steve Goldup from the University of Birmingham. Steve, over to you. Really looking forward to it.
Thanks for keeping the introduction short. I always appreciate that. So I'm going to be talking about the end of the beginning of mechanical stereochemistry. It's a very grand title. So hopefully by the end of this, I'll convince you that that's where we are in the field. So to start though, we have to kind of kick off by saying what the mechanical bond is. So obviously I'm going to be talking about catenanes and retaxanes. So the key things about molecules which are mechanically bonded is, for instance, in the case of the catenanes, we have 2 molecular rings which are threaded through one another, and there's no covalent bond between them, but they can never separate without breaking a covalent bond. So essentially they're linked like links in a chain. And the retaxane, which is the structure on the right, we have a dumbbell-shaped molecule threaded through a ring, and these bulky stopper units on either end are too big to allow the macrocycle to escape. So again, although there's no covalent bond between them, they can never separate without breaking a covalent bond. And these are obviously famously been developed as components of molecular machines, and controlling movement, the ability of the ring and the retaxane, for instance, to move up and down the axle, that obviously led to the Nobel Prize to Feringa and Sauvage in 2016. But when I was starting my independent career, we were thinking about how we could use the mechanical bond. And the thing that really strikes you when you think about these molecules is that by threading one molecule through another, you create this crowded, flexible environment. And we were interested in what we can do with that in terms of the chemistry. And the 2 things you can really do, you can control shape and you can control reactivity and activity. And I'll talk about both of those things at least briefly today. And back in 2014, we wrote a review that kind of set out our kind of philosophy of how we were going to approach this. And it's still my most highly cited review which is a nice thing to have in ChemCom. So if you're interested in the chemistry of the mechanical bond and how the mechanical bond affects chemistry more specifically, I would recommend that as a good starting. And so we've used the mechanical bond to do lots of things. We've used it to control coordination chemistry, to control luminescence, to control supramolecular chemistry, and to control. I'm not going to be talking about any of that today, or at least not in any kind of detail. But what I'm trying to highlight here is the breadth of things you can address with the mechanical bond. So what I'm going to be talking about today is mechanical stereochemistry. And this is a slightly niche area of the mechanical bond, if anything. Even within the field, it seems niche. But it started back in 1961 when Wasserman and Frisch wrote this really excellent review on chemical topology. And there's just a throwaway line. This wasn't even the main point of this paragraph, let alone the main point of the article. But they noted that a catenane where each ring contains two substituents can exist as a pair of enantiomorphs. And they actually credit W. Klossen, who I haven't been able to track down yet. And the system can be considered as analogous to an optically active alene. And this is the diagram they drew on the left-hand side. I'm going to elaborate that diagram ever so slightly now. Because what they're really saying is that if you have two substituents in different positions on the ring, which is these green and the orange blobs, you have the rest of the ring, which I'm representing by this blue blob. When you interlock them, you get a pair of enantiomers. And that's essentially because you have some sequence information in your ring. So you can think of these rings as being oriented. And we tend to use these slightly prettier cartoons to represent this. So this just shows the kind of orange, blue, green sequence within the rings. And if you read Frisch and Wasserman's text carefully and maybe slightly generously, they are also implying that if you put the substituents on the same atoms, a tetrahedral carbon, you also end up with a chiral structure. This is an example of that on the right-hand side. And so you can get a different type of mechanical chirality when the two rings have distinguishable faces. And then in 1971, Gottfried Schill wrote an excellent book all about retaxanes, catenanes, and knots. And it's a book basically of all the things that people have tried and haven't worked, or at least that's the majority of the text. So it's a really excellent read to know the history of the field. And what he noticed was that, as in the case of catenanes, retaxanes may exist as cycloenantiomers which only differ in direction of the ring components. And this is the diagram he drew. You've got R and R prime, so the two ends of our axle are different. And he drew an arrow on his ring, which is to show the ring is oriented. And using our kind of line and blob drawing, this is what we get. We've got the oriented ring, and we've got the two ends of the axle being different. And if we want to go for a slightly prettier cartoon, this is what we tend to draw for these kind of molecules. And he also noticed that if the ring had distinguishable faces, which is represented by this kind of semi-stereocenter or prochiral center, and the ends of the axis are different, you also end up with what we call geometric isomers. So this is the other form of stereoisomerism that Schill identified back in 1971. And this is what I would call the canonical mechanical stereogenic units. We have the topologically chiral catenanes, the mechanically axially chiral catenanes I showed you on the previous slide. We've got the mechanically planar chiral retaxanes and the mechanical geometric isomeric retaxanes I also talked about. And the thing to highlight about these is they're old, 1961, 1971. But actually, all of the chiral examples were being made by chiral stationary phase HPLC separation up until extremely recently. And even mechanical geometric isomers, although lots of examples of these have been published with stereoselective synthesis, almost all of them are based on calixarine or calixarine-like macrocycles. So we were interested in how we can solve the synthesis of these molecules systematically. I'm going to kind of tell the story slightly backwards because I'm going to talk to you about the origin of mechanical stereochemistry. So why is it that when we interlock two achiral components, we can end up with a chiral object? So if we take our cartoon of this oriented macrocycle, hopefully all of you can see that we have a mirror plane which lies flat with the ring. So this molecule is obviously stereochemically trivial. But we've only got a mirror plane that's flat with the ring, and so we call that CNH symmetry. And when you interlock them, Although each ring has an internal mirror plane, there is no way of those internal mirror planes ever becoming coplanar because the mechanical bond prevents the macrocycles from becoming coplanar. And what that means is that none of the symmetry operations of the individual rings survive in the catenane. And so because we can never make the mirror planes congruent, the overall object is chiral. And we can make the same arguments for the rings where you've got two different faces. So now what we have essentially is an infinite number of mirror planes which lie perpendicular to the macrocycle. But when you interlock them, because you've only got mirror planes perpendicular to the macrocycle, none of those mirror planes are symmetry operations of the overall object. And again, because we have no congruent mirror planes that apply to both of the macrocycles, the object ends up being chiral. And these are what we call our mechanically chiral isomers. And when we were doing this kind of analysis, we thought, well, what happens if we interlock these two types of rings? And what you should see is that the mirror plane that lies flat with the oriented ring is also a symmetry operation of the ring with two different faces, because that's got an infinite number of mirror planes perpendicular to the macrocycle. And so this object is obviously not chiral. So we still have a mirror plane which lies flat with the oriented ring bisecting the facially dissymmetric ring. But actually, you can interlock these in two different ways. And because they're not chiral, by default, they're geometric isomers. And we got quite excited when we realized this because we hadn't noticed any of these in the literature. But unfortunately, as we came to write up the paper, we managed to find two examples of these. So using calixarenes, Neri and Secchi and Creedy have both stereoselectively made these types of geometric isomers. But I would argue they're not particularly well conceptualized in the literature. You can play a similar game with the retaxanes, but actually it's quite nice to start from the corresponding catenane. So if we start from our topologically chiral catenane, and we do a thought experiment where we cut this upper ring, and we're just cutting out the blue piece, and we're going to put stoppers on either end, we go through to the mechanically planar chiral retaxane, and this is a chiral object. We've already discussed that. The actually chiral catenane, if you follow the same process and you cut that top ring, you get a bit of a surprise. And the surprise is that the object you get appears to be achiral. And that's because if you put a mirror plane that kind of cuts through the top face of this axle, it's also a mirror plane for the macrocycle. And this is something that we actually hadn't. We'd seen this before, but we hadn't really investigated it. We kind of accepted that there were no mechanically axially chiral retaxanes. But if you draw the catenane in a semi-structural representation, where I'm using these substituents to differentiate the rings, and what we have here is essentially two prochiral rings. If I now rotate the top ring to put the prochiral center into the macrocycle, and then do my cutting, what I get is this object on the right. And it turns out that that object is actually chiral. And so this is a new form of stereochemistry that hadn't previously been recognized. And so what we have here is the mechanically chiral isomers of retaxanes. And then we can play a similar game with our catenane geometric isomers. If we cut the bottom ring, we go through to the canonical mechanical geometrically isomeric retaxane. But if I use the semi-structural representation again, so I'm using this prochiral center to represent the differentiation of the ring faces, rotate the prochiral center into the macrocycle and then do my cutting, I end up with this new object up here. And it turns out that this is a new stereogenic unit. It's another form of geometric isomerism, but it hadn't previously been spotted in the literature. And so this is our set of mechanical geometric isomers. And so if we wanted to kind of try and write down what our target is as synthetic organic chemists, our target is to be able to make all of these stereoselectively. And so we have the catenane geometric isomers, and over the last few years, we've come up with ways of making these things stereoselectively. It's important to note that until our work, you could only make these things using chiral stationary phase HPLC. And the mechanically planar chirotaxanes we spent a lot of time on, so we've got lots of methods for making those. And we've also got methods for making the new stereogenic unit, which is the mechanical axially chiral retaxanes. Taking the geometric isomerism, we obviously have 3 targets here. And actually, we've literally just submitted a paper on this, so we can now make all of these stereogenic units stereoselectively with good kind of 90% DE stereoselectivity for all 3 of these. So we can put ticks next to all of them. We have our chiral ones on the top, our geometric isomers on the bottom, and we've also discovered 2 new forms of stereochemistry along the way using this analysis. And it's relatively easy to prove that this is now the complete set. So the canonical set was obviously missing a few, and now we know what all of our targets should look like. So the rest of my talk is going to be about how we solve these problems in a kind of an overview kind of sense. And this is the reaction we're going to use for everything. So this is just an incredibly efficient way of making mechanical bonds. And it works by taking a copper ion and binding it within the cavity of bipyridine macrocycle. This then ligates the acetylene and the azide component of the very, very famous click reaction. And of course now, because the catalyst is embedded in the center of this macrocycle, the reaction happens faster through the cavity than anywhere else in solution. And we get really, really high yields of the retaxane, up to quantitative, and we can make our macrocycles on really big scale. So this is now a really useful tool for making interlock molecules. So how are we going to apply that in the context of these mechanically planar chiral systems? So this is my oriented macrocycle. If I take my simple half axles, when we're using the active templates, we're going to stick these things together through the macrocycle. We're obviously going to end up making our enantiomers, and those are going to be hard to separate. So that's not going to be a particularly good way of doing this. But if instead we replace one of our half axles with a system that has some kind of covalent stereochemistry, when we form our mechanical bond, we end up with a pair of diastereoisomers. And now these are technically separable using simple chromatographic techniques. And once we've separated them, if we can do some chemistry which erases our covalent stereochemistry, we will go through to our separated enantiomers. And for an organic chemist, this is just a chiral auxiliary synthesis. We're using the chiral information in this simple half axle to derivatize our enantiomers to give diastereoisomers, and then we're using the separated diastereoisomers to make our pure enantiomers. And what does this look like chemically? Well, here is an oriented bipyridine macrocycle. Here is an azide that's got some covalent stereochemistry in it. This is just glucose wrapped up as its bisacetonide. And then this is a simple alkyne, and we can do our active template under relatively standard conditions. And what we go through to is a pair of diastereoisomers. We were very lucky in the first instance, we were able to separate our diastereoisomers. And once we separated them and identified which one we had by crystallography, we were then able to do an aminolysis reaction to cleave all of this covalent stereochemistry and go through to our separated enantiomers. And we're able to get that in very, very high enantiomer purity. So this is the first example of the synthesis of mechanically planar chiroretaxane in high EE without needing to use chiral stationary phase agents. Obviously, we wanted diastereoselectivity in our first example, and so did our reviewers, unfortunately. But after a lot of arguing, they allowed us to publish our paper. But obviously, we worked on this for a number of years, and it did take a number of years. It took 4 years from our first example using this sugar as our auxiliary to getting a high diastereoselectivity using this alpha amino acid derived chiral auxiliary. And you can apply exactly the same approach to the chiral catenane. So this is our chiral auxiliary dangling off the side, and you can imagine we made this using an active template. And in our first example, we managed to get a 50% DE, but actually we can get up to 82% DE, again going to this alpha chiral azide kind of technology. And then more recently, we've come up with a chiral bipyridine macrocycle, which is kind of universal. We can now make catenanes and retaxanes in much greater than 90% EE in most cases. And we've come up with a much more involved synthetic method, which is much more involved, but it's very, very universal. So in this single example, we published 11 examples of high EE retaxanes, and this actually doubled the number of highly enantiopure retaxanes that were in the literature at the time. So I would say that the mechanically planar chiral retaxanes, the topologically chiral catenanes, these are kind of a solved problem. And let's take a break from showing you kind of how we make these to show you why we might want to. And so people have been using these chiral mechanical bonds to do interesting things for a while now. Takata used them to control the helicity of a polymer. Hirose used this mechanically planar chiral host to sense small chiral molecules. Shalai and Baroncini and Creedy have been using these, making chiral switches using the chiral mechanical bond. And this is a really nice example of Wang and Yang, where they used a topologically chiral catenane that had CPL activity, and they showed switchable CPL emission. All of these, though, were made using chiral stationary phase HPLC. So arguably, we still need to get better synthetic methodology out into the community. Just going to show you one example from our group. This is a molecule that Andrew Hurd made. So it's a mechanically planar chiral gold complex, and we applied it in a reaction that was developed by Toast back in 2005. So what Andrew did is he took this gold complex, he subjected it to silver, which removes the chloride, and gave it this propylic ester. And you get a rearrangement of the propylic ester to give you a gold carbene, and that gold carbene can then cyclopropionate alkenes. And under these conditions, Andrew was able to show that just this this conceptually simple gold complex, where the stereochemistry only comes from the mechanical bonds, it's just mechanically steric, just mechanically chiral, could cyclopropionate styrenes in up to 76% EE. And this is the first example of a mechanically chiral molecule being used in catalysis. Okay, so that's kind of our motivation. We think we can use these chiral mechanical bonds to do interesting things in chemistry. How about the axially chiral molecules? So I said that with the mechanically planar chiral retaxanes, when I take my components, I end up with no covalent stereochemistry in them unless I add it in with an auxiliary. But the interesting thing about the axially chiral retaxanes is wherever I cut my axle, I end up with a chiral molecule unless I cut it exactly at the prochiral center into 3 pieces. And what that means is, if I take my 3 components and do a coupling, in theory, I can actually get stereoselectivity directly in this coupling, because we start off with a chiral starting material, and we can use that kind of undergraduate adage, you know, chiral information in, chiral information out. This reaction could proceed stereoselectively. In our first example, we chickened out slightly, and we didn't go for gold. So what we did instead was we changed one of our substrates slightly. And what we've done here is we've made one of the substituents in our prochiral center really bulky. And now when we do our active template coupling, we end up with a pair of diastereoisomers where the macrocycle is trapped on one side of the axial prochiral center. And what you can see, hopefully, is that these 2 diastereoisomers differ just in the position, basically which of these balls is pointing towards the axial prochiral center, so whether it's the blue ball or the orange ball. And obviously these are diastereoisomers, we can separate these. And if we then do some chemistry that basically shrinks the blue ball on our prochiral center, we can then go through to molecules that only express mechanical axial chirality. And what does this look like chemically? Well, we used a sulfoxide unit as our prochiral center in our macrocycle, and we used these half axles. So what we have here is a serine-derived chiral Bock amine, and this is our coupling partner. We react it with this alkyne, and then when we do our active template, we go through to a pair of diastereoisomers where the orange ring is trapped on one side of the prochiral center of the axle due to this Bock group. And these diastereoisomers differ just in whether the oxygen is pointing away from the prochiral center or towards the prochiral center. And once we've separated these, we can remove our Bock group. So we're using very, very standard organic chemistry. And we can go through to our separated enantiomers, where the only stereochemistry now that's fixed is the mechanical axial stereogenic unit. And I think it's fair to say that in our first attempt at this, we were unreasonably lucky, because the active template step works in good yield, and that 61% is really just because it's hard to separate the diastereoisomers, but we are able to do that. And we get a 75 to 25 DR, so we've already got a 50% DE on our first example. And we're able to characterize both of these crystallographically, so we can assign them stereochemistry, and we have good HPLC data to demonstrate the purity of our separated enantiomers on the other side. And exactly the same chemistry can be used to make the catenanes. Again, what we have here is a bulky group. Obviously, this is a chiral molecule that's derived from serine. We've got our azide there, and we've got our alkyne ready to clip round to form our macrocycle. And we can do our active template reaction again with our prochiral sulfoxide macrocycle. We go through to our two diastereoisomeric catenanes, which differ whether the oxygen is pointing up or pointing down. We got even better, as you know, about the same stereoselectivity, so it's about a 40% DE. And then we can remove our bot group again, and now we have a catenane that only has mechanical axial chirality on the other side. So I said that I kind of regretted not going for gold and trying to do a direct enantioselective synthesis, because in theory we could couple these three components in high EE without having to pass through those diastereoisomers. And very recently, that's exactly what we've done. What we did was we put a much smaller group on our nitrogen. And we did our active template at -40, and we were blessed to get a 70% EE under these optimized conditions. And I just want to highlight how this reaction is working. So we didn't really talk about this in our first publications. We didn't have very much evidence. We've now done a couple of structural studies. And what we found is this polarized NH is key for controlling the stereoselectivity. So essentially what's happening is during the mechanical bond formation, we think a hydrogen bond is forming between this polarized sulfoxide and the NH of our protected nitrogen. So if you do this reaction with the amine rather than the formamide, you get a much lower EE. And if you methylate this formamide, the EE drops dramatically. So we're pretty sure it's this hydrogen bond that's directing the reaction. And of course, we have chiral HPLC to demonstrate this. And the 70% EE is this back trace showing that we have one major enantiomer in there. So we're nearly at the last couple of isomers now. So I just wanted to show you what had been done in terms of mechanical geometric isomers of ritaxane, or what I'm calling type 1. This is the canonical mechanical geometric isomerism. So a number of groups have done this, but Arduini, I think, was the first. And what they did was these calixarenes, which have a very, very well-defined set of faces. It's a very complicated looking molecule, but essentially it's very bowl-shaped. I'm just going to abbreviate that in a second to a cartoon. And so what we have here now is a process where we can use this bowl-shaped molecule, and we can form a host-guest complex with this axle, which has two different ends on it. And when we get to that host-guest complex, what we find is we actually have quite a lot of selectivity for the open bowl pointing towards the stopper, and the closed end of the bowl pointing towards the reactive alcohol. And then you can treat this molecule with an acid chloride, and you actually get pretty good stereoselectivity. And there's a whole series of papers. There's some beautiful work out there making calixarene-based geometric isomers of ritaxanes and using those as molecular switches. But actually, we can do this with a single prochiral sentence. So if we take our sulfoxide macrocycle, we do our active template, we can get a disappointing diastereoselectivity. I think it's fair to say 14% DE. But what you'll notice is we haven't really set ourselves up for success here. If instead we do our active template with a half axle that contains an NH, that's now able to hydrogen bond to our sulfoxide unit And actually, this reaction now goes in really good diastereoselectivity. So we can get up to 90% DE in this reaction when we conduct it at minus 40 degrees in THF. So we can control retaxane geometric isomerism just using that single hydrogen bond. And the same chemistry works for the catenane. So we can make our catenane geometric isomers, again, using that single polarized NH to go through to our catenane in 92% DE. And so this is the stereogenic unit we're making here, which is the one that hadn't been necessarily well recognized in the past. And then to finish, I'm going to show you a disappointing result, because this one turns out to be much, much harder to make. So if we take our oriented macrocycle with our prochiral axle in theory, we can go through to our non-canonical retaxane stereoisomers. And so if we take our oriented macrocycle, we take our serine-derived Boc azide, to our simple active template, we can go through under normal conditions to our 2 diastereoisomers. But unfortunately, we only get a 27% DE here. And that's really because the stereochemistry that's in the Boc amine, here, isn't really well expressed enough during the coupling step to give us good stereoselectivity. We have solved this problem using some more advanced chemistry, but I'm not going to talk about it now in the interest of time. But if you're interested, we can get up to 92 or 93% DE to form both of these stereoisomers selected. So hopefully I've convinced you that we've shown how you can make all of these molecules using relatively simple concepts. And I've also shown you that we can use these molecules for things. And so hopefully these two things are now come together, and we're now in a position to start using these molecules to solve chemical problems. And that's why I describe this as the end of the beginning of mechanical stereochemistry. So it just leaves me to thank the organisers for letting me speak today. I'm sorry I've run ever so slightly long, and my group for doing excellent work at all times. It's a pleasure to work with them. I'd like to highlight Andrea, Peter, and Abed, who did the mechanical geometric isomerism. Did the direct active template synthesis of the axially coupled systems. So with that, I'll finish, and I'm happy to take any questions at time.
Great, Steve. Thank you very much. We're off to a good start. Very elegant work. Again, for questions and answers, as I've posted in the chat, for an attendee, if you wish to ask a question, just raise your hand. Alternatively, you can put the questions into the Q&A box down the bottom there of the webinar, and I'll read it out for you. I don't see any there just now. So maybe I'll kick off, Steve, with the first question, if that's all right. Very elegant work, and it's nice to see new elements of, not new elements of chirality, but new examples of, let's say, axial and planar chirality away from the binap systems, or away from the ferrocene di-substituted systems. And you applied one of them, a gold complex in asymmetric catalysis, which is interesting to me, because that's what we sort of focus in on a little bit. Gold is a hard it's not always the easiest to get high levels of stereoselectivity because of the the bond angles being 180 degrees and all that. Have you tested the monophosphine with any other metal in any other transformation?
Yeah, I mean, you've just articulated why we did the project really well, so thank you for doing that. I didn't have time when I was going through, but it's hard to impose a chiral environment around the substrate in a gold catalyzed reaction. The mechanical bond gives you that free, so that's the good. The bad is that molecule's horrific to make because it was made before we had a lot of our newer technologies, and so we haven't investigated it in a huge amount of detail. We started doing some palladium complexes of those types of systems, and we're starting to look. So again, we've done some other work in an achiral gold system where we were able to control the diastereoselectivity of a reaction by binding things into the macrocycle cavity, and we were able to optimize the diastereoselectivity for different substrates with different additives. And that's actually where we want to go with the gold catalysis, to try and use supramolecular chemistry to kind of re-optimize your gold catalyst, to try and tweak it for the substrates you're using. We've had some success is the most polite way I can put that, because it hasn't turned into a paper, right? So it works, it doesn't work well enough. But I think now that we can make these things more easily, not only can we start to actually investigate them more intensively, we could also maybe start to understand how the stereoselectivity is arising. So we need to marry this with computational chemistry quite desperately, because honestly, you look at this molecule, it looks very, very flexible. There's lots of bits to it. It's actually very hard to explain how you get any stereoselectivity. And so we need to kind of get a broader understanding of how that's working as well.
Great. Thanks, Steve. I don't see any further questions coming through. Any questions from the panelists, co-speakers? Time for one short question.
I can ask a quick one, Pat, if that's all right.
Of course.
Yeah, thanks, Steve. Do you have plans to move to other metals? We can't hear you, Steve. Oh, I can't.
Yeah.
Okay.
No. Now we can.
Okay. Don't know what happened. My computer is doing strange things this morning. That's why I was running a little bit late. So we're doing some stuff with iridium and rhodium at the moment, from a slightly different perspective, because Eric Meggers has developed some beautiful at-metal chiral systems. And they're beautiful, but they're kind of limited in what you can make, because essentially everyone uses these kind of unsymmetrical bidentate ligands to construct the chiral metal system, whereas we can actually use the mechanical bond to engineer the coordination environment pretty much at will. And so we have an example now where we can make a single stereoisomer of a metal system where technically every single ligand is different. So it's fully heteroleptic, and we've played some tricks there. I'm giving you very much the cell, but we're now investigating how we can use those in catalysis, and also in optical materials.
Thanks, Steve.
Okay, thank you.
Okay, in the interest of time, maybe we'll move on to the next speaker. Super,
Yep.
Steve.
Thank you.
Okay, so the next speaker is Amanda Jarvis from the University of Edinburgh. Amanda, are you able to get yours? Yeah, brilliant. Things are happening. So I think we just need to get into present mode. Excellent. Okay, Amanda, the floor is yours. Very much looking forward to it.
So thanks very much for the invitation to speak to everyone today. And yes, we're going to move on to some similar aspects as what we've just heard, but also a few different things as we're now into proteins. So one of the sort of aims of our group or objectives is that we kind of set up for ourselves is, can we bring classical industrial chemical reactions into the biocatalytic toolbox? And our interest in doing this is, could we take kind of what's typically viewed as sort of quite dirty industrial reactions, high temperatures, pressures, and take advantage of sort of the greener side of enzyme catalysis, their selectivities, their use of ambient conditions, and water as a solvent. And so I started in this area in my second postdoc, where we were looking at hydroformylation, which I'm sure many of you will agree is a classic industrial reaction. And the concept was, if we could put a rhodium catalyst within a protein where we had an sort of apolar pocket, as Hunnell, could we end up doing selective hydroformylation where we would get the linear product as opposed to the branch product, and could we do this under biphasic conditions? So typically, if you're going to your longer chain alkenes for hydroformylation, these aren't very soluble in water, and so you have to use phase transfer catalysis. And so we were able to show that we could do this by building up a phosphine within a within a protein through cysteine modification. And we were able to get through to reasonably good turnovers of sort of 400, whereas if you used a small molecule catalyst, they were much lower if you were still going to get up to kind of 80%. So if you use the sulfonated triphenylphosphine. So this is quite exciting. I won't go into much more detail as this is all published, but we also showed that the sort of resulting rhodium hydroformylase that we designed could also be kind of engineered as you would classically would for enzyme engineering, so we could look at improving the thermostability by introducing salt bridges and various changes, and in turn that also allowed us to increase our temperature of reaction and increase our turnover numbers. So this was all sort of started in Paul Karma's group at the University of St Andrews, and we continued to collaborate once I set my independent group. Unfortunately, he has since passed away, but we are still working on this sort of area, looking at taking our feedstocks and seeing if they can be more bio-based feedstocks going forward. But that's one aspect of what we look at. But today I'm going to tell you a slightly different story about new active sites and proteins. So kind of a key part of that work was this idea of really bringing in a different metal site into a protein. So there we were using malamide chemistry to bring in a phosphine, which you would never normally find within an enzyme or within a protein environment. And from that phosphine, we could complex it to kind of all the classic late transition metals. In this example, we're looking at radium. But when I set my independent group, we were also interested, what else could we do? And one idea was artificial unnatural amino acids. And if we could combine all these different approaches to maybe bring in some really new to nature active sites and enzymes. So just to give an overview of what's sort of done in this area, there are a couple of different approaches to really designing new metalloproteins or metalloenzymes. Probably one of the most successful or well known to date is repurposing of enzymes. This is kind of a top-down approach where you take an existing metalloenzyme and you can see if you can go towards other reactions, other transformations, or indeed changing the metal that you would naturally have there. So can you replace in iron heme? Can you replace your iron with iridium and so forth? At the other extent, we have de novo enzyme design, which is kind of a bottom-up approach where you just kind of design around your metal, or for an enzyme, a new protein fold, a new environment using predominantly canonical amino acids to do this. Though some unnatural amino acids can also be done. And this would allow you to get something very different potentially than what would exist in nature. And then finally, there's sort of a middle way that sits between the two, which is kind of commonly referred to as artificial metalloenzymes. So we saw an example that I showed earlier was a covalent modification where we were using a cysteine to introduce a synthetic metal cofactor. This can also be done supramolecularly, and this has kind of been exemplified by the work of Thomas Ward in particular with biotin and streptoavidin. Or you can begin to think about using non-canonical amino acids, unnatural amino acids, to add new functionality to your protein that might bind metals in a different way and different metals. So this is the last area, is what I was going to talk to you today. So if you think about the amino acids, there's a number of them that you would think about as ligands, so your histidines or your aspartic and glutamic acids in particular. And if we go into the non-canonical amino acids, these have really sort of expanded in the last 20 years. Of people have worked out how to introduce these using cellular machinery as part of what's referred to as the expanded genetic code. So I think to date, over 300 amino acids have been incorporated into proteins through expanded genetic code methodology. But what I've shown here is kind of the handful of these which actually bind metals. So you can see there's some quite classic types of ligands shown here, sort of bipyridine, phenanthrene, and intriguingly, very recently there was a report of a protected phosphine as well. So if we look at one of these, bipyridine, bipyridine itself is a well-studied ligand. Many of you will be familiar with it. We already saw bipyridines in a different context in the earlier talk. And and it's got multiple applications when it's bound to metals across catalysis, medicine, and materials. And this means it's been one of the most studied probably within the field for this area. And I've just shown a few examples in the literature where people have used bipyridines with metals to either kind of control structure of a protein assembly, control dynamics, or build up monomeric metal centers with new types of binding. And so when I started my group, our question was quite simple. Could we introduce bipyalanine into a protein scaffold? I hadn't ever done genetic code expansion before, so this was our first target. So the protein scaffold that I'm going to talk about for the rest of this course is the one that I was working on, or we stuck to the same one that I'd worked on as a postdoc, so the steroid carrier protein 2L. This is a human protein. Things we look for in a protein structure is that it's got a known structure and it's easy to produce and modify. So this is a depiction of the protein itself, and what you can see very clearly is there is this kind of linear tunnel that sits throughout the protein structure. In the crystal structure, this actually, to get the crystal structure, you need to add triton, which is this molecule shown in red, and that sits within the tunnel. It's a relatively small protein. It doesn't have any cysteines in it naturally, and its crystal structure was known, so that gave us a good starting point with how we could change it. And we knew that it was amenable to both cysteine modification and genetic code expansion, or we found out, so that was good for us. So we were looking at introducing our bipyridine. In the talk, I'm going to show you two different ways we did this. So first, I'm going to just show you the kind of more classic way where we use bioconjugation. So if we have introduced a unique cysteine into our protein at the desired position, we can either react with a malamide or with an alkyl halide to get through to bipyridine modified proteins. The malamide reaction is slightly cleaner than the alkyl halides, but in both cases we get through to a pretty much fully modified protein that we can then play around with different metals and look at what we can do. For genetic code expansion, we have a slightly different system to go through. So I'll go through this for those of you that are less familiar. So in genetic code expansion, when we're growing up our cells, we have two plasmids within our E. coli, and one plasmid is providing the cell machinery needed to allow us to now incorporate our unnatural amino acid at a tag codon or UAG codon, as opposed to it reading stop. So we're using amber stop codon suppression. So what you need to provide is these orthogonal amino ace cell synthetases and tNRA that are only going to recognize your unnatural amino acid and place that efficiently at this codon. And then the rest of the amino acids are encoded using the standard translation system. And what this allows you to do is build up a polypeptide with the amino acid of interest, or non-canonical amino acid of interest, at a very defined position. So then we also have a plasmid that contains a protein gene and with a tag codon where we want it. And just to note, we put a his tag on the C terminus, and this allows us to purify only the proteins where we have read through the stop codon with our unnatural amino acid. We won't purify out any shortened proteins where we weren't successful at suppressing the stop translation. And we also have present is a TEV cleavage site so that we can remove the his tag so that that's not going to interfere with any subsequent metal binding. So if we grow up our E. coli, when we want to induce gene expression and start producing our protein, we need to add in our non-canonical amino acid. This is a slightly sad part of the procedure, so we have to synthesize our bipialanine, and we need to use around 160 mg per liter of this material before getting through to purification in our protein of interest. And per liter of media, we're getting around 10 mg of protein, so we're actually throwing away quite a lot of the bipialanine. So that's something that we're looking to improve in the future. So does it work? Well, yes, we've managed to do this where we've introduced bipialanine at a number of different locations along our protein tunnel. And by mass spec, we see very clearly that we get our expected masses. So that's all nice. We do see a drop off in yield compared to the cysteine mutants, and this is due to like the stop codon suppression not being completely optimal. So we are still reading stop in some cases. So what we wanted to do, now that we both had a protein which had a bipyridine on it from alanine, so from genetic code expansion, and one where we'd modified our cysteine, was we wanted to look at what were the differences between these. In particular, in catalysis, did we see any differences that we could use or benefit from? Because there's slight differences in the ease of making or taking each approach that might determine which one you'd use for any given application. But first we had to show that we could bind a metal. So we chose copper as a starting metal. And so here we can just see if we titrate in some copper nitrate, you can see very clearly that we lose the UV bands associated with the bipyridine itself, and increase those when from the copper complex, and we're getting essentially 1-to-1 binding. More excitingly, we were able to get crystal structures for 2 of our metalloproteins. So these are where we had the bipyridine in the 1-1-1 position. So this is sort of midway along that tunnel. And so here we've got the cysteine that's been modified with bipyridine. You can see very clearly it's binding its copper. And we've got some nearby interactions helping to stabilize where the ligand sits. And in a similar way with the bipyridine alanine in the 1-1-1 position, we can see again we've got copper binding very nicely. And so these, I guess from if you're used to the small molecule crystallography, it's a crystal structure and it's nice, but this represents one of very few examples that are now in the PDB which show an unnatural amino acid binding to a metal. So it's nice to be able to add that to the data that could be used for future attempts at designing new proteins. So with our copper metalloproteins in hand, we wanted to look at some catalysis. We chose this reaction as sort of a benchmark. It's been explored in the literature by a number of other groups. So we felt we knew it should work quite well, but it also would give us a sort of a comparison to other artificial metalloenzymes with how it worked. And what you can broadly see is if you just have bipyridine and copper, or just even copper sort of and the protein together in solution, you get moderate yields, but no enantioselectivity. And then once we've introduced our bipyridine, either by the cysteine modification or by genetic code expansion, we can see that we now are seeing some evidence of enantioselectivity. Of particular interest is probably this last one, which happened to be the one we also had the crystal structures of. So this is Q11 bipiana, where we actually see a 20/80 enantiomeric ratio. And if you compare that to the pretty much all the other examples, that's also a switch in selectivity, and particularly a switch compared to when we've got the cysteine modified bipi in the same position. And if you compare the two crystal structures, this is probably, or this already shows that this might not be a surprise, as you can see that they are orientated quite differently in a sort of almost mirror image type way once you overlay the crystal structures. And both of them are sticking externally to the protein, which wasn't entirely what we were expecting, as we designed the system to maybe have the metal site within the tunnel, but we see them on the outside of the tunnel. So Julia Richardson was the crystallographer for this work, so that was really helpful. And then Havis also looked at doing some calculations to see if we could get any further information about these sites. Whilst we could kind of confirm that computationally and experimentally we got the same sort of enantioselectivities, we didn't see very many sort of interactions with the surrounding amino acids. And alongside alanine scanning studies we've done, we haven't really identified any key residues. So optimizing this further from the sort of 60% EE has proved quite a challenge. So this was all the work of Eva, my first PhD student, and Richard, my first postdoc in the group. So I'm going to move on to a slightly different topic here, which is cyclic peptides containing unnatural amino acids. So whilst I was at St Andrews, I saw quite a lot of the work from Jim Naismith's group, where they had were interested in macrocyclization, and they'd discovered this PCY1 macrocyclase, which could do macrocyclization of pregabalin B1s to give these small macrocycles. And what they showed is you could use it over a much more widely varied set of peptides and include sort of unnatural features. So I'd always been interested in if we could use this to incorporate actually a sort of a metal ligand somewhere in a macrocycle to get through to potentially asymmetric ligands based on cyclic peptides. And if you look here, we could see if we could replace our tyrosine with one of our unnatural amino acids, we were interested to know, would PCY1 still accept it? So these were the amino acids we chose to look at. And this was a project really driven by master's students in my group, Katrina and then Arati. Katrina had brought the kind of peptide synthesis experience to my group from a previous project, and so was able to synthesize all these peptides. In this case, we just use a shortened leader unit, so FQA, which is what the cyclase will recognize, and we were able to show that within the cyclase, it would accept actually any of these amino acids to get through to your cyclized peptide. And we were able to get this through in pretty good conversions and reasonable isolated yields for a cyclic peptide. So once again, we looked at the cyclic peptide with bipyridine with copper binding. We were able to show the copper did bind. And once again, we looked at the same catalysis. We were able to get through to our product, but we essentially observed no enantioselectivity. And this is perhaps not surprising because the peptide we're designed for checking that it could be incorporated and expressed by the PCY1 enzyme, and not because we were designing kind of the best asymmetric ligand. So we think that we could do that by kind of thinking more carefully about where we place ligands, other amino acids going forward. So have we looked at any other metals with these systems? So as I mentioned, bipyridine's been involved in lots of different types of metals. Classically, you might think about things like the ruthenium trisbipi as a photocatalyst, or sort of piano stool complexes such as these, either as catalysts or in medicine. So we have also looked at these, again, both with our malamide protected or bipialanine containing protein, where we looked at in making some of the pianostool type complexes with iridium or ruthenium. Again, using mass spec to kind of show that we were able to bind or make the starting material. And then with ruthenium, we can see evidence of binding our metal complex. It's not maybe the most compelling evidence for getting through to a single metal complex. So we did look essentially to applications to maybe show this. And if we look at transfer hydrogenation, we can see, although BIPI itself is not a classical ligand for this transformation, we do see that in the presence of our protein with the bipyridine in different sites, we are able to see some enantioselectivity and turnover, which is quite an interesting initial observation that we're still looking to see where that increase in yield and enantioselectivity comes from. However, the last part of the talk that I'll say is about when we looked at genetic code expansion using bipyridine alanine, essentially the same conditions, but we've got our protein where we've used genetic code expansion to introduce the bipyridine. We saw 0 yield for any of our proteins, including the wild type, in what are pretty similar ligands or catalysts. And we were wondering why we kind of didn't see the sort of same results and why we saw the same regardless of whether we had bipyridine or the wild type. And it made us think about some of the differences in our gene construct. And what we realized is we'd introduced an N-terminal methionine to the gene, and we knew this could potentially bind metals in a bidentate or maybe even tridentate method. And indeed, if you just look at ruthenium complex with a protected methionine amino acid, you get the same result. I realized that 0 yield is not the most compelling. We also did this on the iridium work, where in this case what we saw was similar yields and the same enantioselectivity regardless of our catalyst. So providing more evidence to us that we thought we had N-terminal methionine binding. And we could also turn to analysis to check this. So this is a little bit of top-down mass spec data, where we showed that actually, if you look at sort of the Z ions that you see, that sort of allows us to identify that potentially our metal is binding somewhere in the first 5 residues of our amino acid. So what did we do? Well, we thought maybe if we remove our N-terminal methionine and replace it with a glycine, we could get rid of this activity, and maybe there'd be a chance that it would actually bind to our bipyridine instead. We could do this by adding an N-terminal TEV cleavage site, which would replace the first 2 amino acids, methionine and glutamic acid, with a glycine. And on doing this, what we found was that for most positions, we seem to get results now consistent with ruthenium and bipyridine, so very little activity. But in one position, we're now beginning to see an increase in yield. So we think this provides further evidence that we really did bind a ruthenium to our methionine N-terminus, but we're still trying to get more data. That's obviously not a result we wanted, but potentially is interesting because any protein or many proteins have N-terminal methionine because methionine is your start codon. So thinking about how we could maybe use this observation in different ways or in catalysis in a different way. So in summary, hopefully I've showed you that genetic code expansion allows chemists to build up new complexes and proteins. I think there's quite a lot of exciting opportunities, particularly for organometallic chemists in this area, about bringing kind of new reactivities to proteins. And although I sort of focused on kind of catalysis as one of the aspects, I think there will be observations that we see that might have provide solutions in sort of health and materials as well. So none of this work would be possible without my group. So I'd like to kind of thank all of them, in particular, Richard and Eva, who really started some of the work on the unnatural amino acid stuff, Gaurav and Isabeau have also been working on some of the ruthenium and iridium work that I showed, and Katrina and Arati were key in the as EuChemS students in the cyclic peptides work. None of it would be possible without analytical help, particularly Julia Richardson for X-ray crystallography, and Faye, Logan and Dave for the mass spec work we did. And finally, thank you to these people for funding, and thank you for listening.
Great, super. Thank you very much, Amanda. And again, it's open for questions and answers from the attendees. So again, I remind people to either raise their hand or submit their question into the Q&A. So Steve, you can just ask your question straight away. Yeah, that's easiest. You're a panelist.
Thanks a lot, Pat. EEs are nice. I know they're not what you want them to be, because everyone wants 99%. But it's nice to see anything, right? Because it's very hard to define what you're going to get before you make it.
Yes.
Did you look at any other substrates other than that fluoro one? Because it seems quite specialist.
For the transfer hydrogenation, no, we didn't look at any other substrates yet, because essentially we got sidetracked by this idea of where the metal really was, and whether we were even making what we wanted. So I guess we spent more time kind of trying to look at, can we understand the metal binding than substrate scope, but it is something we'll go back to. I lie when I said we didn't try any other substrates. We did try, I think, the non-fluorinated substrate, but that doesn't work at all. These aren't the best catalysts for transfer hydrogenation in general, so that is a very activated substrate for that.
Yes, the reason I was asking was because obviously you could have specific non-covalent interactions between the substrate and the protein. You haven't really set yourself up for any there. I was just wondering if you thought about how you could engineer those kind of interactions into the system.
Not yet. I think that would be the next thing if we find out whether it's solely, if we can move it away from just being an N-terminal methionine that's binding, where we think we're only getting it from the methionine chiral center, any enantiomer induction, and that's the N-terminus is quite floppy, so it doesn't show up on any of our crystal structures. So we're not sure we would have a very defined environment in that case. I think, yes, if we got it onto the BIPI substrate scope and seeing if we could control it more would be of interest.
There's potential for enzyme-like behavior, right? Where you get very specific substrates working because of the very detailed local environments. It's really, really nice stuff.
Yeah. Thank
Great.
you.
Thanks, Steve. Maybe, Amanda, I could ask a question myself, and it's nice to see the work you've done as a postdoc with Paul. I interacted with him when he was still in Amsterdam, and he was a real gentleman, and he's a loss to the chemical community, there's no doubt. He was one of life's fine gentlemen in the chemistry world. So my question relates to the work you did with the copper catalyzed Friedel-Crafts alkylation. We've worked a lot on bidentate systems in this transformation and found that zinc actually was far superior to copper.
Okay.
Did you ever try zinc as your catalyst for that, as your metal, I could say, for that?
No, we've never tried zinc.
Yeah, might be worthwhile having a look at that.
Cool, thanks.
Okay, we have a question coming through in the Q&A, and it's from Maxime Vitali. I hope I pronounced that correctly. For the transfer hydrogenation, when you get 22% yield, does it mean that at some point the hybrid protein gets degraded, or that the reaction is incredibly slow?
Probably the reaction is incredibly slow. So I'm guessing it's relating to this particular reaction. So we briefly mentioned this. So it's an interesting result, this. Bipyridine itself kind of seems to shut down this reaction. which would maybe imply we had some 3-ruthenium. But our EE in this case, and we've repeated this a number of times to check, is very high, which would indicate a defined binding site within the protein. Due to the sort of the subsequent work we saw with the methionine, we haven't managed to confirm so far that that's definitely on the bipyridine. That would be your initial assumption from the sort of set of work we did, because that's what's changing between the 3 different proteins and ligands, is that you're changing area. You'd expect it maybe to bind to a bidentate ligand, and we just have built up a very defined location, but we're not sure. So we don't know whether it's just very slow, we don't know.
Okay, great. So perhaps in the interest of time, we'll stop there. Thank you very much, Amanda. Back over to you. Oh no, there's another question. Hold on, sorry. Oh no, thank you. That was the answer from Maxime, so it's not a question.
Okay.
So she thanks you for that answer.
Thanks.
Well,
Okay,
thank you
Will.
very much, Amanda. So next we have Stephen Clark from the University of Glasgow. Stephen's slides are appearing as I speak.
Okay.
Over to you, Steve.
Right. Thanks, Will, for that. And let me start off by thanking the organisers of the event for a very kind invitation to tell you a bit about our chemistry. It's really appreciated. I'm glad to be able to contribute to this feast of chemistry. So, as Will mentioned right at the start, we have a long-standing interest in the synthesis of complex natural products. And the compounds that I really want to talk about today are ones that we've been working on for more years than I care to remember, but certainly since the late 1990s, we've had an interest in making these very complex polycyclic ether natural products. So what I've shown on the first slide are just some examples of this, just to give you just get my pointer on. There we go. Just to give you a sort of flavor of the diversity of these compounds, there are some very large structures in this family. There are dozens of these compounds known. They're sort of prototypical members of the brevetoxins, but since the early 1980s, there have been a host of other series of compounds isolated. Compounds come from marine dinoflagellate organisms or from higher organisms that feed on the alga. What I want to talk about today is CTX3C. These compounds, well, CTX3C, like other members of the family, is a potent neurotoxin. Some of these compounds also have some beneficial activities. So, for example, the gambaric acids, which we're also interested in synthesizing, are very potent antifungal agents. And Brevinal is actually a lead compound for the development of new agents to treat cystic fibrosis, and in fact, other diseases of the lung, including COPD. So some of these compounds do have beneficial activities, but primarily they are potent neurotoxins, and they act by disrupting ion channels in nerve membranes. So as I said, the compound I'm going to talk about today is CTX3C. And CTX3C was first isolated in the early 1990s from a culture of a dinoflagellate that was collected in French Polynesia. So the name of the organism is Gambierdiscus toxicus. It's a potent neurotoxin. The LD50 for a mouse is between 1/4 and 4 micrograms per kilogram of mouse. Given that your average mouse is so small, that's actually a very, very small amount of material that's required to kill 50% of the mice. It binds, as I say, to voltage-sensitive sodium channels, and it results in persistent activation. So what that means is the nerve membrane cannot re-establish membrane potential. The ion channel is left in an open state, and that means that the effectively the nerve doesn't function anymore. So in terms of synthetic challenges, I think it's pretty clear what's the difficult aspects of this molecule are. First of all, one has a number of rings here joined together, transfused. The ring sizes range from 5-membered up to 9-membered. So the 7, 8, and 9-membered rings in the middle here, and also the 8-membered ring over here, are particularly challenging structural units to synthesize. There's a total of 30 stereogenic centers, and 2 of those are quaternary. So there's plenty to go at in terms of stereo control in this any synthesis of this compound as well. So the landmark synthesis in this area came about from the group of Hirama in the early 2000s. He was actually able to synthesize CTX3C by a fairly convergent approach. Having said that, his synthesis is still 50 or 60 steps, longest linear sequence. So it's a pretty long synthesis, and pretty remarkable that he was able to complete that with the team that he had assembled. Okay, so our approach is to go also through a relatively convergent approach late in the synthesis. So what we want to do is to build two polycyclic fragments and then join around the G and H rings over here. So if we open the G ring at this position here, remove the methyl substituent here, branching methyl substituent, and open ring H, we get back to this propylylic ketone system. And in the forward direction, the key reaction after joining these two units about this bond here is going to be a nucleophilic attack on the alkyne, so a formal 7-endo-dig cyclization onto this unit here to give the G ring, and the final ring closure will be through ring H. If we cut through this bond here, we get back to these two fragments. We get a hexacyclic fragment on the left-hand side, that's the A to F fragment, and a pentacyclic fragment on the right-hand side, which is the I to M fragment. So what we're trying to do here is go for two fragments of roughly equal size and complexity, which will build up in a stepwise fashion, or perhaps by joining small units together, and then do a grand sort of coupling of those two units to make this system, and then close, as I say, rings G and H. So to explain how we're going to make the fragments, I just need to tell you a bit about some chemistry we developed 4 or 5 years ago. And we discovered that making cyclic ethers using ring closing metathesis was a reasonably good proposition, but the issue was how one functionalized the cyclic ether unit afterwards. And we alighted on the asymmetric Tsuji-Trost allylation reaction as a way of installing the side chain that we need for further functionalization. So what I've shown on this slide is some work we did, which was really inspired by the work of Brian Stoltz, where he had developed these Fox-type ligands for controlling the absolute stereochemistry in these reactions, starting from achiral substrates. In our case, we found that starting with a single enantiomer of the cyclic ether unit up here, we'd formed by metathesis, we could generate the enol carbonate shown here, and then have that undergo the Tsuji-Trost reaction by treatment with palladium. And again, we've chosen here to go using the Fox ligands, and we looked at both enantiomers of the Fox ligand and also this dimethyl Fox system here, which is an achiral Fox equivalent, to work out what the innate diastereoselectivity of these systems were without the addition of a chiral ligand. So what we found was that with either R as hydrogen or methyl here, with the achiral system, with hydrogen, we get about 2-to-1 ratio of the two diastereoisomers shown on the right. So there's a weak substrate bias in favor of the diastereoisomer that we require for the polyether series. We can enhance that by using the ST-butyl Fox ligand. And so now we have matched catalyst and substrate control, which gives very high selectivity for the compound that we require. Interestingly, we can actually turn over the natural substrate bias by using the other enantiomer of the Fox ligand, using the R Fox system. In that case, we can generate this other unnatural diastereoisomer with reasonable selectivity. So this weak substrate bias can be turned over by choice of catalyst ligand. In the case where we have a methyl substituent here, we generate a quaternary center, the same sort of pattern applies. So now with the dimethyl Fox system, the achiral catalyst system, the substrate bias is a little bit higher in favor of the isomer that we want. When we match that with the catalyst choice, well, we get very high selectivity again, and we can do partial switch over by going to the R-butyl Fox system to give the wrong diastereoisomer. If we go to the 8-ring case, similar trends are observed. So again, we can start off with a cyclic ether with the hydrogen or methyl at this position here, and make the enol carbonate, do the same Tsuji-Trost asymmetric allylation reaction. And again, with the achiral system, we get about a 2-to-1 preference for the isomer that we want. We can enhance that by doing using the matched catalyst system. We can turn it over using the mismatched system. In the case where we have a methyl substituent, the preference again is slightly higher or considerably higher using the achiral ligand. So it's about a 9-to-1 preference without any ligand present, or with a ligand that's achiral rather. And we can enhance that using the ST-butyl-FOX system to give essentially one compound. Now, because the substrate preference is higher to give the compound that we want, it's a more difficult job to turn over that selectivity. So using the mismatched catalyst, we get about a 1-to-1 mixture. So we're not able to turn that over and override this natural substrate bias completely. Okay, so that's the enabling technology. How does this fit into the synthesis? Well, for the A to F ring fragment, first of all, we've recognized we could disconnect the F ring to get back to this pentacyclic fragment, which presents a hydroxyl group and this allyl substituent here. And this is now set up to do the Suji-Trost chemistry that I showed on the previous 2 slides. So if we cut through here, this implies a metathesis disconnection. Remove the ether, remove the allyl group, that's the Suji-Trost allylation disconnection. When we do that, we get back to this tetracyclic fragment, which presents exactly the same architecture at the end over here as in the previous case. So now we have an allyl group and a hydroxyl group. And again, we apply the same disconnection here, ring closing metathesis disconnection, Suji-Trost disconnection, and a standard ether disconnection over here to get back to this tricyclic intermediate. And we felt by disconnecting that, we could get to this sort of modified carbohydrate type system, which would represent the B ring fragment. So the synthesis starts with this glucal derivative, which is easily prepared from D-glucal. We protect with this NAT protecting group, and the reason we chose that group was this is the protecting group that Hiram had used in his synthesis. He'd found some issues at the end with deprotection using things like PMB protective groups, and so he found that this NAT group was actually a good choice. So rather than reinventing the wheel, we went with the NAT group, and that allowed us also to compare some of our intermediates with his during the synthesis that I'll come to in a moment. So taking this enol ether, we can then do a DM-duo oxidation. That's highly diastereoselective and is controlled by this group over here. And then open that glucal epoxide with allyl magnesium chloride to give the alcohol. We then simply allylate the alcohol, perform ring closing metathesis, and that generates the 7-membered A ring of CDX3C. We then remove the acetonide. We can make using tosic acid. We can then make the triflate and at the primary position and test protect in one pot to give the triflate shown here. We then open that with lithium TMS acetylide, install an alkyne. TBAF deprotection gives a terminal alkyne, and then Lindlar reduction under control conditions gives the allyl group here ready for the next metathesis reaction. We then convert the alcohol into an alkynyl ether using this procedure here. So we go through a trichloroenol ether and then treat that with butyl lithium. This is a procedure originally developed by Andrew Green and his group in Grenoble. We've used this over many years, and it's a really good way of making alkynyl ethers of secondary alcohols. We can then perform a ring closing E9 metathesis to give the diene system here. So this is quite an efficient route until we get to this point. And what we found was that ring closing E9 metathesis in this particular system, whether it's because we already have an alkene present in the substrate or for some other reason, this tends to be rather variable in terms of yield, and the yield really is rather modest. So anywhere between about 40 and 60% is possible, but yields tend towards more the 40% end of that spectrum. So we were a bit unhappy with that, and we decided to come up with an alternative route here. So starting with that triflate I showed 2 slides ago, we can displace that with the anion of T-butyl acetate. And what we can then do is take the product compound here and reduce that to give the diol, do a tempo-mediated oxidation to convert that into the lactone, convert the lactone to the enol triflate, and then do a Stille coupling under standard conditions with vinyl stannane to give the same diene that I showed on the previous slide. And this route's much more scalable. It doesn't suffer from that low yield at the end, as we saw in the case of the metathesis chemistry. So in terms of bringing material through, this is a far more reliable route. What we then do is selective epoxidation of the enol ether portion of this diene system. That's non-selective in terms of stereocontrol. And then we can open with, under reductive conditions, BF3 etherate with trithylsilane. That then gives a mixture of isomers at this position here. So hydride delivery comes in axial on the carbenium-ion intermediate. So we get good control of the stereochemistry here, but no control of the stereochemistry here, obviously, because we started off with a mixture of epoxides. Desmartin oxidation and then reduction gives us a single diastereoisomer of the alcohol that we want. So we correct that stereochemical issue. Now we're ready to enter the first sequence of metathesis and sucrose allylation. We first of all alkylate this alcohol with this chloroketone. So this is quite an unusual system because we've got a phosphonium ylide embedded in this system already. So we can alkylate here and then use the resulting phosphonium ylide to react with formaldehyde to give the enone on the right-hand side. Ring closing metathesis of that diene system then gives the cyclic ether. And we can now functionalize this using the sucrose chemistry that I showed before. So now we need the R-2-butyl FOX ligand to match the substrate here. So we make the enol carbonate, form the sucrose allylation reaction. That goes very nicely. You get very high selectivity for the diastereoisomer I'm showing here. Luce reduction of the enone then gives us the alcohol. And we're able to crystallize this compound and get an extra crystal structure to confirm that we've made the desired compound. What we then did was to repeat that sequence. Having done it once, we then go through exactly the same sequence again, reacting with the chloroketone, then Wittig reaction with the resulting phosphonium ylide. Ring closing metathesis, that works quite nicely, 63% yield. And then we can make the enol carbonate, react with R-2-butyl FOX, palladium complex to give the rearranged product here. And again, we get very high levels of diastereocontrol control in that reaction. And then Luce reduction gives us the alcohol. So we use this 5-step sequence twice to get through to the, first of all, the 7-ring system up here, and then the 8-ring system down here. Now to make the 9-membered ring, we have to do something slightly different here. We react with this bromoester, alpha bromoester, and then cleave in situ the ester group to give the carboxylic acid. And then we use Evans chemistry here to control the stereochemistry in the subsequent alkylation reaction. So what we do is we introduce the oxazolidinone auxiliary. We then deprotonate at this position here and react with bromoacetonitrile and then reduce off the auxiliary to give this alcohol. The ratio here, the diastereomeric ratio for that is about 8:1. The yield is not good. We get a lot of recovered starting material from this reaction. So that's the true yield, unadjusted for recovered starting material. So the yield is probably nearer 40 to 50% when we recover the starting material. What we then do is oxidize the alcohol and do an allyl-stannane in addition to the resulting aldehyde. That gives a mixture of diastereoisomers without really much selectivity at all. And then we perform ring closing metathesis on that to make the 9-membered ring. And we oxidize to get rid of this stereocontrol issue here to give this ketone. And it turns out that ketone is crystalline compound. And so we're able to get an X-ray crystal structure to confirm that everything had been installed as we expected. Some interesting features in this system. You notice here how sort of rigid in terms of conformation this system appears here. And also over here, we've got this twisted system in this 8-membered ring. So from a structural point of view, it's quite fascinating to see how this system adopts the conformation it does in the solid state. Okay, so that completes the A to F fragment. What about the I to M fragment? Well, just to take you through the retrosynthetic analysis here, the last thing we're going to form is this acetal. So if we open that retrosynthetically, we get to this diol system. The diol we felt we could make from the alkene by dihydroxylation. If we reorganize this allylic ether to give this enone system, where the enone is actually part of an enol ether, then again we can cut across here and we can get back to a similar disconnection that I showed in the first slide where I was talking about the whole molecule. So we're going to use this addition onto an probagilic ketone at this position here to form the 7-membered ring. We're also going to use that when we've joined the fragments together to form the G ring in the synthesis. So we're going to use this chemistry twice. So this is a good opportunity for us to try out this chemistry early on in the fragment synthesis before we commit to doing this in the after the final fragment coupling. If we chop off here and then reconnect, we get back to this lactone, this gamma lactone. If we remove the methyl substituents, open the lactone, we get to this 8-membered cyclic ether system. And again, this is now set up for the ring closing metathesis and CG-Stross combination of reactions to construct that ring as well. So that's the I ring. And this connection further then gets back to this simple starting unit. So we've made this alcohol previously from a carbohydrate. What we can do is then exactly the chemistry I showed previously, alkylate with that chloroketone and do a catalytic reaction with formaldehyde, then perform ring closing metathesis. However, what we found was that a reduction with sodium borohydride first was required before doing ring closing metathesis and then reoxidation to get viable yields. We can do the straightforward RCM of this directly to this compound. The yields are actually really poor in that case. And that's a bit surprising given we've already used this to make an 8-membered ring in the AHF fragment synthesis. And it just shows that subtle conformational differences seem to make a big difference in the success or failure. This is not a particularly good group to react at an RCM reaction. And here we're trying to make an 8-membered ring at the same time. Obviously, we've just tipped the reaction away from success towards failure. So we have to reduce that, which adds actually 2 or 3 steps, or actually a couple of steps actually, which is not great, but we have to do it. Then what we do is make the enol carbonate, and now we're using the ST-butyl-FOX palladium catalyst, and rearrangement of that system gives 14:1 preference for the diastereoisomer that we want. We then add in an organocopper reagent generated from methyl lithium and copper iodide. So conjugate addition occurs highly stereoselectively. We reduce the ketone using Dibal, and what we find is we get a crystalline compound, and we were able to confirm the structure by X-ray crystallography. So we can show that we'd actually installed this methyl substituent and the hydroxyl group with the required stereochemistry. What we then do is protect the hydroxyl group, and then remove the acetonide protecting group to then chain extend further or to build up further rings. And we do that by making the triflate of the primary hydroxyl group, displacing that with cyanide ion to give the nitrile. And then we do Dibal reduction and reoxidation to give the carboxylic acid. It is potentially possible to get from here to here, but we found this is a much better route, more reliable route for doing that rather than trying to do direct hydrolysis, saponification of the acid formation from the nitrile. So having made the carboxylic acid, we can then close that to give the gamma lactone using Yamaguchi conditions, and then we alkylate, so deprotonate with LHMDS, react that with methyl iodide. That unfortunately gives us the wrong diastereoisomer as the major product. So what we then do to correct that is deprotonate and then quench, and that gives us the compound on the right here, where we've got the methyl group now with the correct stereochemistry at this carbon. We then took the opportunity to set up the side chain ready for coupling. So here what we do is we dihydroxylate and then cleave the 1,2-diol in situ using sodium peroxide, give the aldehyde. We then reduce and protect to give the protected system over here. The lactone is then opened using lithium borohydride to give the diol system over here. And then we double test protect that system. Now we want to extend the side chain over here, and because we've chosen to use TES groups, we can employ a Swern oxidation here without deprotecting first. So Swern oxidation of primary TES protected systems, TES protected alcohols, you can directly get to the aldehyde. So we don't have to mess around with protecting groups here. We can just double protect and rely on Swern oxidation to allow us to oxidize at this position selectively with the remaining TES group intact on that secondary hydroxyl group. The side chain that we need to couple, we can make starting from this C2 symmetric diol. This is a compound that's easily prepared. We can monoprotect that to give the alcohol on the right. What we then do is Des-Martin oxidation to the aldehyde, then use the O'Hara-Bestman modification of the Seifert-Gilbert reaction to give the alkyne. Remove, here we did a protecting group interchange for reasons I don't want to go into, but we took off the silicon protecting group and we Pivalol protected that to give this compound down here at the bottom left. And then we can make the iodide of the alkyne using iodine and morpholin. And that gives us the alkynyl iodide ready for coupling. So what we do now is we take our aldehyde we formed and we do a Mizaki-Hiyama-Kishi coupling with the iodide, and then reoxidize the alcohol and remove the TES protecting group to give the alcohol up here. So we're now ready to try that first 7-ring formation using addition to the alkynyl ketone. And the procedure we opted to go for is this gold catalyzed reaction that Uchiyama and co-workers published 7 or 8 years ago. What they showed was you can actually use this on this very simple system to generate exactly the type of ring system that we want to construct. Now, our system is a bit more demanding than theirs. The yield here is already what you describe as modest towards modest. We're a bit concerned because we've got this rather congested system up here at the terminus of the alkyne. We've got 2 branch points here next to each other, and one's next to the position at which we're only going to go nucleophilic attack. We also have a substituent here, so this is not necessarily in the right conformation for this system to cyclize easily. So we were slightly nervous when we tried this reaction. However, our fears were unjustified. We found that, in fact, we got a much better yield than in the model system published by Uchiyama. So using exactly his conditions, we were able to cyclize effectively to give this enol ether. What we then did was we hydrogenate the enol ether to give the saturated system and converted that compound into the enol triflate. And what we then do is reduce out the triflate using the palladium catalyst in the presence of formic acid and a triethylamine. So effectively just reducing this system out, making the organopalladium, and then having that reduce out to give the alkene. So this is kind of an alternative approach to doing a Bamford-Stevens or Shapiro type reaction, where you would convert the ketone directly through the tosyl hydrazone into the alkene. What we're doing here is we're doing this under milder conditions, making the enol triflate and then reducing that down to give the alkene. And then finally, what we do is a dihydroxylation reaction using the Shal plus admix beta system to install the 2 hydroxyl groups that we here need on ring K. So that's where we got to with that fragment. What we need to do to complete everything would be to acetonide protect, cleave the ester, oxidize this up and add in the appropriate side chain, then reoxidize the alcohol here and perform acid catalyzed deprotection and spiroacetal formation. However, we don't want to do this too early in the synthesis. So although I'm showing you what we'd have to do to make the complete fragment, we are probably going to take through the system in this form or this form here and make the spiroacetal at the end. The reason for that is after we've coupled, we need to do some Lewis acid mediated chemistry to build particularly ring H. And we don't want to have a problem with competing reaction of this rather sensitive spiroacetal system. So although this is the complete fragment, we'd probably take this through in partially complete form to couple to the A to F ring fragment. Okay, so that's where it stands today. I just want to finish up by thanking the people who actually did the work. So in particular, the 2 postdocs, Miron and Venki. Miron, he did all the A to F work, and Venki did the I to M fragment synthesis. So they were in my group from about 2019 onwards. Unfortunately, they were heavily impacted by COVID, so we had the whole COVID fiasco take place during their time in my group. So that I really felt that held them both back in terms of getting further with the project. Earlier work was done by Helen, who did some of the early methodology work on the RCM chemistry. Mike Popadinek, who did some earlier versions of the synthesis of the I to M fragment. Sam, who did some of the original work on the A to F fragment. Jim, who did all the model work on the Suji-Trost annihilation reaction. And finally, Sophie, who's just finished her PhD in my group, and she did some of the tidying up work on the A to F ring fragment. I'm grateful to Claire for providing backup in terms of X-ray crystallography. We really rely on her very heavily to confirm or determine the structure of intermediates that we prepare. Without her work, we wouldn't be able to do what we do, I think. And then finally, for financial support, the EPSRC for funding Miriam and Venki, and also some of the PhD students, and also the University of Glasgow for some PhD support as well. So thanks to all these guys. Thanks again to the committee for the invitation to speak today. And thanks to everybody for listening. Thank you.
Great. Thanks very much, Stephen. And we're open now for questions. We have one coming in from Maxime again. Thank you, Maxime. Fantastic work. Thanks a lot for your talk. As it seems, you've been consistently using Grubbs 2 catalyst for the ring closing metathesis. Considering that your substrates display several CC carbon-carbon unsaturations, I assume, do you have any chemoselectivity issues leading to partial degradation? If so, would you not achieve better chemoselectivity with Grubbs 1 or the Hoveda Grubbs catalyst? So that's the question.
Okay, so we have actually used Hoveda Grubbs catalyst in some reactions, and sometimes we get slightly better yields, sometimes it doesn't make much difference. But the question about unproductive or competing reactions is a really good one. So we were quite surprised, particularly when we formed the D ring, and we were making that 7-membered D ring, and we were making the 8-membered E ring. So maybe I can just go back to back. The point. Let's go backwards. Yeah, once we'd made yeah, so at this point here, we used the Grubbs 2 catalyst. I can't remember if we actually tried Hoveda Grubbs in that system or not. I think we probably did have a look at that as well, and it didn't make a great deal of difference. But you're right, there's an issue here about this potentially, if we initiate here, that reacting with this alkene over here. Let me get my laser pointer on again. That potentially reacting with this alkene. I think the reason that doesn't happen is we get initiation preferentially here, and then this is actually conformationally not set up to react across, even though technically it's 1, 2, 3, 4, 5. This is pointing out to a completely different region of space. This ring kind of keeps this away from this alkene here, so it reacts over here. So we don't really see any problems with that. Where we may have an issue is when I showed you the ring closing E9 metathesis reaction, where we get very modest yields for that. And what we may be getting is ring opening of the A ring alkene in that reaction as well. We have used the first generation catalyst in that system, and the yield was actually poorer than with the second generation catalyst. And I'm pretty sure we also looked at Hoveda Grubbs for that, and it didn't make much difference to that system either.
Great. Joelle, I think you also have a question.
Yeah, nice talk, Steve. Thank you. I wanted to ask about the Evans calculation. Did you try any of the other auxiliaries, or is Valine the best one, the best compromise between yin and selectivity?
Right. Okay, that's a good question. As you know, we both worked with Dave Evans. The phenylalanine derived auxiliary was king, right?
Yeah.
We don't really need to have a UV active chromophore in that system, but also we did think about other auxiliaries, but we were really short of material. We're already 25 steps or so in at that point, so we didn't exactly have an awful lot of material to go with. So the postdoc Miron, who did the work, he went for that auxiliary in preference to any of the other auxiliaries. I mean, we could use Myers chemistry. We could, a whole host of other auxiliary groups we could use there, but we didn't have the luxury of being able to do a a nice screen of all the different chiral auxiliaries for that reaction. So no, we didn't really try anything else.
Okay, thanks.
Great, Steve. Maybe if I could, Stephen, if I could ask a quick question. I mean, the palladium catalyzed decarboxylative asymmetrical alkylation is one of your key steps in the synthesis, and you've always used the sort of Stoltz-derived cyclic enol carbonates. Did you ever investigate the corresponding beta-keto allyl esters as an alternative way to form that? So that
we haven't in this project, but we are in another project, Pat. Yeah, we've actually done some other work again with ether systems in another total synthesis using the beta keto ester systems, and they work well as well. We've got pretty good levels of in that system. We're starting off with an achiral cyclic ether system, so we have no resonant stereocenters on the substrate in which we're doing it, and we're getting pretty high E levels between 85 and 90%.
Is that with the Stoltz ligands or with the Trost type ligands?
With the Stoltz type ligand. And we are going to look at other ligands for that system. You see, the thing about the systems I'm showing here is that we already have, it's already a chiral molecule. We're just enhancing the diastereoselectivity. So whether it's 24:1 or 20:1 doesn't really matter so much. But when in systems where we're starting off with a completely achiral substrate and using this as the key point at which to make the molecule a chiral molecule, we want to enhance that EE further. So yeah, we are going to have a look at some of the other options and perhaps look at some other newer ligands, maybe design some ourselves that we will test on that system. So yeah, you're right. There are lots of other opportunities there.
Yeah, we've certainly found the anden phenyl Trost ligands to be optimal for the enantioselective systems.
Right. Okay. Right. Okay. Well, they'll certainly be on our list, but thanks for that tip.
Okay, good. So back over to you, Will. Thanks, Stephen.
Thanks, but thank you very much, Stephen. So next we're on to here we go. I can see Rebecca Neelan from Cardiff University. So Rebecca, if you are able to share your slides, please.
Is that okay?
Something's happening. Yep, that looks perfect. Thanks a lot, Rebecca. The floor's yours. Really looking forward to it.
Good, thank you very much. So yeah, thank you very much for inviting me to give a presentation. So today I want to talk about some of the work that we've been doing very recently on radical frustrated Lewis pairs. So in our group, we're interested in main group chemistry, and we're interested in using the main group elements for catalysis for reactions that are typically performed using transition metals. And we don't want to replace transition metals. They're very good at what they do. But what we're more interested in is understanding the reactivity of the main group elements, and also to see if we can find complementary or alternative reactivity to what's done using the transition metals. So today I want to talk to you about frustrated Lewis pairs, and in particular, radical frustrated Lewis pairs. So to give you a brief introduction, so normally if you have a Lewis acid and a Lewis base, then you would get donation of your lone pair from your Lewis base to your Lewis acid to give you a classical adduct. Now, in a frustrated Lewis pair system, you don't get adduct formation, and this is typically due to steric hindrance. And so what this means is that you still have your lone pair present on your Lewis base and your vacant orbital present on your Lewis acid, which we can use for small molecule activation and catalysis. And the idea here is that this is similar to transition metals, where you have vacant and filled orbitals, which you can use for small molecule activation. So the key paper in this field was published back in 2006 by Doug Stephan, and he reported the synthesis of this compound here, which is a frustrated Lewis pair, because we have a Lewis acidic boron center and a Lewis basic phosphorus center, and in solution, this compound doesn't dimerize or form an adduct. And the key results from this work was that this compound could reversibly activate hydrogen. And this was the first metal-free compound that was known to activate hydrogen reversibly. So you could take this molecule here, add hydrogen, you get the borohydride and the phosphonium cation. And then if you heat up this compound, you can release hydrogen to give you back the starting material. And so this has been very important for activation of different small molecules, and also in metal-free hydrogenation catalysis. However, if we look at the mechanism of H2 activation, so normally with transition metals, you get a homolytic process. However, with frustrated Lewis pairs, typically you get heterolytic hydrogen cleavage. So if you have your Lewis acid and your Lewis base, initially what happens is the two compounds come together to form what's known as an encounter complex or an EDA complex. And then in this system, what happens is your lone pair from your Lewis base will donate into the sigma star of your H2 molecule, and then the electrons from your sigma bonding orbital in H2 will donate into the vacant orbital of the Lewis acid to give you the product. However, in 2011, Warren Peers suggested an alternative mechanism, which is homolytic cleavage of H2. And the proposed mechanism was if you have tertiary butyl phosphine and tris pentafluorophenyl borane, or BCF as the Lewis acid, then initially you could get single electron transfer from the Lewis base to the Lewis acid to give you the phosphonium radical cation and a boron radical anion. And so this is known as a frustrated radical pair. And then the idea here is that then you can get homolytic cleavage, again, to give you the same product. However, in this publication by Warren Peers in 2011, this was suggested to be a very unlikely pathway due to the large difference in redox potentials between the Lewis acid and the Lewis base. And this was also later confirmed by Chris Slutberg, who said that the lifetime of these radicals is very short, and so you can easily get back electron transfer from this intermediate to the starting material. So in this case, it's most likely that you're getting heterolytic H2 cleavage. However, more recently, frustrated radical pairs were shown to be formed when you have this nitrogen compound as the Lewis base. And here you can get single electron transfer from your lone pair of your nitrogen to the boron center, and you can generate this nitronium radical cation, and you can see this by EPR spectroscopy. However, in most cases, and this is the same in our work as well, we don't see the boron radical anion because it is so unstable. So more recently, Doug Stephan has revisited this work with the phosphorus Lewis bases and also boron and aluminium Lewis acids with pentafluorophenyl groups. And in the EPR spectrum, you do see the formation of the phosphorus radical cation. But again, in the case of boron, we don't see the boron radical anion. But if you switch this to aluminium, then you can see the aluminium radical anion. However, again, calculations by Chris Slutberg said that this is not possible thermally because the difference in energy between, this is the ionization energy of the Lewis base to give the phosphorus radical cation, and the electron affinity of the Lewis acid to give the boron radical anion is too high to happen under thermal conditions. However, it was proposed that you could get this to happen under UV light. And so initially you get the formation of the EDA complex, as was proposed previously, and then you can generate the frustrated radical pair. So this was the initial studies into the mechanism of generating these frustrated radical pairs. What we've been interested in is in the reactivity of frustrated radical pairs. And so this is very recent work that dates back only sort of the last 3 or 4 years. And one of the key early papers in the fields was by Oy, who looked at using these frustrated radical pairs for CC bond forming reactions between amines and alpha beta unsaturated ketones. And what he found is that in the case of this TMS substituted amine, then you could get single electron transfer between your Lewis base and your Lewis acid to generate this frustrated radical pair. And in this case, again, you can see the ammonium radical cation by EPR. And then this molecule here can react with your alpha beta unsaturated substrate to give you the CC bonded product with elimination of the TMS cation. However, if you then move to other amines, so without the TMS substituent, then this reaction doesn't happen thermally. So I should say in this case, this will happen in the presence of irradiation or thermally. But in the case of this amine, then you have to use irradiation, and this reaction doesn't happen thermally. But again, you can get the formation of the frustrated radical pair and then CC bond formation when you add in the substrate. More recently, so this year, Song Lin has also published a paper in Nature on frustrated radical pairs. And this is a very nice paper which starts off by using the HDMS anion and the temperate cation. Initially, you get single electron transfer from the nitrogen to the temperate cation, and this gives a very reactive transient radical, and also this more stable persistent radical. And this has been shown to be very selective in CH activation of a variety of different CH groups. So just to give you an example with this molecule here, so using this system where we have the temperate cation and the HMDS anion, we can get, or they showed that you can get very selective CH activation to generate this product here, which could then be further functionalized either to give the alcohol or the ketone. So this is a very new field that's only been going for the last sort of 5 so years. There are a few reviews out on the topic now by ourselves and also Song Lin. So if you're interested in this, then all of the results are shown in these few reviews. So how did we get into this field? So initially, when I started at Cardiff, we were interested in using this Lewis acid, so tris-pentafluorophenol borane, to activate pi bonds in a similar manner to precious metals such as gold or palladium. And so we were interested in this paper by Suzanne Blum in 2009, where she showed that you can use gold as a Lewis acid catalyst to activate this triple bond, and then you can get cyclization and migration of this group attached to the oxygen from oxygen to this position in the product. And so we wondered if we could get similar reactivity using these boron Lewis acids, where the boron activates the pi bond. And so this worked very nicely. We could use 5 more % of the catalyst, which is the same as what was used with the gold-based catalyst. And we could get cyclization of these types of systems to give us these heterocyclic products. And this worked well for a variety of different substrates. So we could do this with saturated backbones, we could do it with an aromatic backbone, or also with just a double bond. But in terms of the functional group at this R1 position, this either has to be a proton, or it has to be a group that can easily stabilize a positive charge. So we have either a 1 RR group or 2 RR groups. And so what we propose is that this is going via a cationic pathway, where this group is migrating from oxygen to carbon. What we can see here is that with just 1 RR group, then we get a much lower yield. And also with deactivated alkynes, again, so with this para CF3 group, then again, we get very low yields. So this was the initial study that we had in the area. But one of the problems with this reaction was that we had to synthesize all the starting materials. And so my student wondered if you could do this in an intermolecular process. So just start off with the ester molecule and an alkyne, cleave this carbon-oxygen bond, and then get addition of these 2 groups across the alkyne. And in our case, we couldn't get this reaction to work, although Martin Österreich has recently shown, just by altering the substrates, that you can get this reaction to work. However, when we tried this, we didn't see this reaction. And so what my student did was he decided to take a frustrated Lewis pair approach to this reaction, and to perform this reaction, but also adding in a Lewis base. And what he found when he did this reaction is that he isolated these crystals here, which was due to this phosphonium borate. And so what happened in this reaction is it looked like we had cleaved this carbon-oxygen bond, and the ester portion of the molecule had coordinated to the boron. In reaction, the diphenylacetylene hadn't reacted, and also we were unsure where this phosphorus had picked up this hydrogen atom from. And it later turns out that this is actually coming from the solvent. So we went away and we looked at this reaction again, removing the alkyne from the equation and just looking at the reaction of the ester with a variety of different Lewis pairs or frustrated Lewis pairs. And what we find when we do this reaction with a variety of different phosphines is that what we think happens is the boron coordinates to our Lewis basic oxygen center. We then cleave this carbon-oxygen bond, and then the cation that we generate is trapped by the Lewis base. And we can see this if we look at either the phosphorus or the proton NMR spectra. We see a clear 2J pH coupling between the phosphorus and this hydrogen atom. And we can see this if we look at the proton NMR spectra on the right-hand side. For most of these phosphines here, we get this clear doublet from this pH coupling. But when we look at mesotylphosphine, you can see from the in situ spectra, we don't see this doublet. So we went away again and we looked at this reaction again with trimesotylphosphine. And what we find happens is that, again, as I showed on the previous slide, we can isolate this phosphonium borate salt. And then what we did was we took the remainder of the solution from the reaction and we recrystallized this. And what we found is that it was the dimer of the other part of the molecule. And so this led us to believe that perhaps this reaction in the case of the trimesotylphosphine is going via a radical mechanism. And at the time, we did this work just after Doug Stephan had proposed this frustrated radical pair mechanism between trimesotylphosphine and tris-pentafluorophenyl borate. And also, when we look at the reaction, we get a very deep purple color. And at the time, it was thought that this was due to the phosphonium radical cation. So we went away and we did some EPR studies. This was done by Emma Richards at Cardiff University. And we clearly see this doublet, which is due to a phosphorus-based radical. And if we zoom into the middle of the spectrum, we see a very weak signal, which we attribute to the carbon-based radical. So what we think is happening here is that we're generating the radical portion of this molecule, and that it is dimerizing to give us this homocoupled product. So we then thought, well, what could we do with these reactions rather than just getting the homocoupled product? And so we thought, well, could we react this carbon-based radical with both alkenes and alkynes? So first of all, we looked at reactions with alkenes in an sp3-sp2 coupling reaction. So taking this carbon-based radical and adding it to an alkene to generate this carbon-carbon bond. And this works very well. So we do this in THF. So we switch the solvent from CDCl3 or toluene to THF. And we do this for 1 day, and we can form this carbon-carbon bond. And as you can see, the yields are sort of average to quite good. And we can do this for a range of different aromatic substituted alkynes. What's interesting is with this last case, when we use alpha methylstyrene, we get 2 different isomers of the product. And what's interesting in our case is that the major isomer that we generate is the opposite to what you generate when you do this in a transition metal catalyzed reaction. We also looked at this reaction with alkynes, so in an sp3-sp coupling manner. And again, we can get CC bond formation for a variety of different aromatic alkynes with different substituted esters. And again, the yields of these reactions generally between 60 to 90% yields of the products. So we then wondered, well, what is the selectivity between the 2 different reactions? So if we have both an alkene and an alkyne, will we preferentially get reaction with the alkyne? Will we get reaction with the alkene? Or will we get a mixture of both? So first of all, we did the reaction and threw in both an alkene and an alkyne, the other way around. And we reacted this with our frustrated Lewis pair. And when we do this in both, we do 2 solvents, and we'll see why this is important later. When we do this in both THF and trifluorotoluene, what we find is that we get exclusive reaction with the alkene, and we see no product, alkyne, and we see no product for reaction with the alkene. We also looked at intramolecular systems, and again, we see the same reactivity. So when we have the alkene and the alkyne in a para-substituted fashion, in all cases, we get exclusive reaction with the alkyne, and we don't see any reaction with the alkene. However, what was very interesting was when we switched the substrate and we now look at the ortho-substituted aromatic system. And what we find here is we get solvent-dependent selectivity depending on whether we do the reaction in trifluorotoluene or THF. So first of all, when we do the reaction in trifluorotoluene, then we see exactly the same as what we saw previously, and we get exclusive reaction with the alkyne, and we see no product for reaction with the alkene, and we see none of this double substituted product. And this is also true if we do the reaction in toluene, which will become important later. If we then switch the solvent to THF, what we find now is that we get different selectivity. So when we switch the solvent to THF, now we get, as our major product, we see a reaction with the alkene. So this is our major product in the reaction, although this reaction is less selective, and we do see a small amount from reaction with the alkyne. And in one case, so in this the methyl case, we see a small amount of this double substituted product. And I should add, when we have the paramethoxy substituted starting material, then we don't see any reaction at all. So we're then wondering, well, what is the mechanism for this reaction? Is this going via a diamagnetic pathway, or are we going through a radical pathway using frustrated radical pairs? So we propose two different pathways. So the first diamagnetic pathway is where the boron coordinates to the oxygen atom. We generate the boron, the borate anion, which we see in the crystallographic studies. And then we generate the cation and the phosphorus. We have our phosphorus Lewis base. And this could act a bit like a frustrated Lewis pair, and we can get addition of these two species across the alkyne or the alkene. And then in the final step, we get elimination of the phosphonium cation and generate the product. If we look at the radical pathway, then we propose the initial step is exactly the same, where we get coordination to the ester, elimination of the borate anion. And then we propose that we have three species in solution. So we have this species here, which we could consider as a frustrated radical pair. Lewis base could donate to the cation to generate what we could consider as an adduct. And then we propose that if we cleave this bond homolytically, we can generate the carbon-based radical and the phosphonium radical cation, which I'll show later we see in the EPR studies. This can then the radical can then add to the alkene or the alkyne, and then in the final step of the reaction, the phosphonium radical cation can abstract the hydrogen atom to generate the product. So we do some EPR studies. I won't go through this in detail, but essentially we see evidence for both the phosphorus, the carbon, and also the boron-based radical in the reaction. However, the question is, are the radicals actually involved in the pathway that leads to the product? And so what we did was we did some calculations to investigate the mechanism for this reaction. And similar to what Chris Slutweg found in his previous studies, is that the energy to generate the radicals just between the Lewis acid and the Lewis base is too high to happen under thermal conditions. So what we propose initially happens is we generate this cationic species, as I showed in the mechanism, by coordination of the boron to the ester functionality. And then these three species in solution are very low in energy. So it's likely that we have a mixture of these, the frustrated Lewis pair species, the adduct, and the frustrated radical pair present in solution. And so this could explain why we're seeing these radicals in the EPR studies. So we then looked at the addition of the cation and the radical to the alkyne. And what we find if we look at the transition state, so this is the radical pathway on the left and the cationic pathway on the right, the transition state for addition of the radical to the alkyne is much higher in energy than addition of the cation to the alkyne. So what we propose is that in this case, the reaction is likely going via a cationic mechanism. We also looked at this by changing the substrate, so changing the para position on our substrate. And as expected, if this goes via a radical pathway, then you won't see much change in the activation barrier. So we can see this here. Whereas if this is going via a cationic pathway, you'll see a large difference in the activation barrier. So with electron withdrawing groups, you see a much higher activation energy, whereas with electron donating groups, you see a lower activation energy. And so what this means is that when we have electron donating groups, this is almost exclusively going via a cationic pathway. However, when you have electron withdrawing groups on your substrate, we could start to see a radical pathway taking place. In addition, we also looked at changing the R group on the ester, so this R1 group here. And in the case of when we have a para CF3 group, what we see now is that the radical pathway, the transition state energy for the radical pathway is now lower than the cationic pathway. So what we think in these reactions is that generally they're going via a cationic pathway, but for some substrates, we might start to see a radical mechanism taking place. We also looked at this experimentally. So by taking our ester starting material and two different substrates, and what we find in these reactions is that in all cases, the more electron-rich substrates react preferentially. So for the paramethoxy substrate, this will react preferentially to just phenylacetylene. And so we can see that in these results here. The final thing we looked at for this was to understand the selectivity when we change the solvents. And so what we looked at was the reaction of the cation that we generate with both the alkene and the alkyne in THF and toluene. So we see the same reactivity in toluene as we see in trifluorotoluene. And what we find when we do the reaction in toluene is that our transition state energy is much lower for reaction with the alkyne than it is for reaction with the alkene. And so that's why we see exclusive reaction with the alkyne when we do the reactions in toluene or trifluorotoluene. But when we switch the solvent to THF, then we see a reverse in the activation energy. So now the activation energy is lower for reaction with the alkene than it is for reaction with the alkyne. However, this is very similar, and so this could explain why these reactions are less selective. So that was the results from our first study in this area. The problem with this study is that our Lewis acid or frustrated Lewis pair that we're using stoichiometrically. And so more recently, what we've been doing is looking at catalytic reactions for CH chalcogenation reactions. And so hopefully I'll have enough time to talk you through this. So what we've been interested in is reacting aromatic systems with N-thiosuccinamides. And what we found is that we can do this reaction very easily to generate this carbon-sulfur bond in very good yields using 10 mol% catalytic loading of our boron Lewis acid catalyst under very mild conditions, so 45 degrees C after just 2 hours. And this reaction works very well. So we've looked at the aromatic scope of both the starting aromatic material and N-thiosuccinamide. And you can see the yields of these reactions are very good. And we can also do this reaction with selenium instead of sulfur. We can also do this, and this is quite important with these systems, with coordinating groups such as nitrogen or alcohols. And these are usually problematic when we have our strong Lewis acid, as they tend to coordinate to our Lewis acid catalyst. We've also looked at the other scope of the thiol, so we can do it with other aromatic systems and alkyl systems. And also importantly, we can do it with SCF3 groups, although we see lower yields of these products. And again, we've shown that we can use this for late-stage drug functionalization of these two different drug compounds. If we look at other scope, we can do this with other aromatic systems. So it works well with nitrogen heterocycles, getting substitution at the C3 position. However, if we switch to benzofurans or the thiofurans, then what we see is the reactions are less selective, and we get a mixture of either C2 or C3 substitution unless we block one of these positions. So what else can we do? So we've looked at drug synthesis. We've looked at the synthesis of this antidepressant compound. So we can do the first step of this reaction on a larger scale, generating this intermediate in 68% yield. We can then do a Buchwald-Hartwig coupling to generate this intermediate, and then deprotection finally gives us this drug product. We've also used this towards the synthesis of these heterocycles. So again, we can do this first step of the reaction on a larger scale, generating this intermediate in 78% yield, and then do a cross-coupling reaction, copper-catalyzed cross-coupling reaction to generate this heterocycle in 67% yield. So finally, what we've looked at is post-synthetic modifications. So what can we do with these compounds once we've generated them? So we can do various oxidations, either to the sulfone or the sulfoxide, using MCPBA. So if we have an excess, then we'll get the sulfoxide. And if we just use one equivalent, then we can get the sulfone. And we can also generate the sulfoxamine. Finally, what we've looked at is cross-coupling reactions. So when we have the substrate with this parabromo compound, then we can do a variety of different cross-coupling reactions at this position. So what's the mechanism for this reaction? So we're wondering again whether this is going via a cationic or a radical pathway. So first of all, we did some EPR studies using PBN as a radical trap. And what we see here is that we're generating the succinimide radical, which is trapped with the PBN, and we can see this in the EPR studies. And also, if we don't use the radical trap, then we can see the boron coordinated to the N-succinimide radical. What we propose is the first, also if we use radical scavengers, such as tempo or an alkyne, then we see a massively reduced yield in the reaction. So what we propose is the first step of the reaction is initial coordination of the boron to our N-thiosuccinimide substrate. And we can see this if we look at the NMR spectra of this compound and compare it to the adduct. So we see a de-shielding of this carbon position, this carbon atom from the starting material to the coordinated product. And we also see a shift in the boron NMR spectra from the boron starting material, which usually is a broad peak at around 60 ppm, to a broad peak at around 0 ppm. So just quickly, we have looked at the mechanisms for these reactions computationally, and we've looked at both a cationic pathway and a radical pathway. And currently the energies of both pathways are about the same, so we can't currently say whether it's going exclusively by a radical or a cationic pathway. So this is the pathway we've calculated for the cationic pathway with an energy of 21.4 kcal per mole. And with the radical pathway, we have two proposed pathways. One is via a concerted radical pathway via an intermediate like this. And then the second one is like a two-step pathway where first of all, we see a reaction with the aromatic system to generate this aryl radical, which is then reacted with our sulfur radical to generate the product. And you can see here the energies for this 23 and 23.1 are very similar between the radical pathway and the cationic pathway. So that brings me to the end of my presentation. So I've shown that if we have phosphorus Lewis acid and a boron Lewis base, then we can potentially get the formation of frustrated radical pairs in the presence of the substrates that we're using in our reactions. And I've shown that we can use these in CC bond forming reactions and also in CS bond forming reactions. So finally, I want to thank the people that have done the work. So a variety of former group members who have started this project, and current group members. Milan has done a lot of their work with the N-thiosuccinimides. Rasul has worked a lot on the calculations, and PhD students Kate and Samperna have worked on these projects. I'd also like to thank various collaborators for EPR studies and computational studies. I'd like to thank the EPSRC and Liebe Trust in particular for funding, and thank you for your attention.
Super. Rebecca, thank you very much for that. That was a really interesting presentation. And again, it's open now for questions from the audience, either from panelists or any of our near 120 participants that are attending. So again, either raise your hand or use the Q&A function. Maybe I could start off with a question, Rebecca. I mean, very interesting stuff to see how you can now make carbon sulfur bonds by using this methodology. Does it have any, I'd say, advantages over some more modern or more other methods for making carbon sulfur bonds, like palladium catalyzed reactions? I mean, are there substrates that this works for the palladium doesn't, or vice versa, or is it complementary? So there's a sort of...
we haven't really compared it as yet. So we're still currently writing this manuscript. Hopefully we'll submit it next month. I mean, the advantage of this system is that, I mean, we can do this, these reactions only take 2 hours, very mild conditions. Yeah, we do need to look at comparing substrates to other systems to see if we can do substrates that can't be done using palladium or other metals. That we still need to do. But yeah, the advantage of this system is that it's very very mild. But yeah, we're still looking into that.
Any other further questions from panelists? In common with many of the Highlighting Organic Chemistry series, we're woefully poor at time management, so we're a bit over. Will, I'll blame you. Only messing. Any other questions coming through? Sorry, Rebecca, there doesn't seem to be. So maybe if you don't mind, we'll leave it at that, and over to Will to introduce our next speaker. Thanks, Rebecca.
Thanks, Pat. So we have Duncan Brown up next from University College London. Duncan is already loading up his slides very efficiently, which will help us with the time. So Duncan, looking forward to your talk. The floor is yours.
Lovely. Thank you very much, Will, and thanks for the invitation. Just to reassure myself, can you hear me and can you see the slides okay?
All good.
Yeah, looks good.
Lovely. Thank you. So today I want to talk to you about our adventures in mechanochemistry. We started out in this area in about 2015 or 2016. And I think we're getting to an understanding of the different scales and variations of mechanochemistry now. So I wanted to sort of share that with the people on the webinar today. So if you haven't seen mechanochemistry before, a few slides here will give you a brief introduction to it. So it really comes in two different flavors. So I use these diagrams to try and explain what they are. So the blue square represents a mechanophore. That is a central motif in a molecule that is undergoing mechanical action. And so in the far left hand side, we can pull on this mechanophore and induce usually a braking reaction, so a retro-aldol or retro-Diels-Alder reaction. And you would achieve this by using atomic force microscopy or sonication, where the bubbles are growing, and applying your forces to the mechanophore. And things are quite subtle and have to be very delicately designed and engineered in the molecules that you're going to apply this to. But what we're doing is far less subtle, in that we are applying compressing forces through pulverizing materials inside a ball milling device. And one aspect of this is that we are getting mechanical activation of bonds, but we cannot decouple it necessarily from thermal activation of those bonds as well. We can't also decouple it from application of shearing forces, where we have crystal particles rubbing off from each other and exposing fresh faces of either reactants or products. So with this in mind, ball mills have been used quite commonly in a range of sciences, and actually synthetic chemists are probably one of the last sciences to be adopting them. Universally, they've been used for the fine particle reduction of samples, so essentially to homogenize samples of rocks, homogenize drugs with their excipients, or to grind things like tissues and teeth in a forensics lab. Here we're not only interested in that, we're also interested in trying to perturb a bond to affect a change in its energy. Depending on the type of mill that you use will determine which forces are going to be applied, and historically this was all done with a mortar and pestle. But the problems here is that the stamina that any operator has will vary between those operators, and the energy input is also going to vary. So you can change this, and you can essentially plug this into the electric and power this in a thing called a ball mill. So the idea is you put your materials inside a jar, and then that jar is shaken back and forward, and the ball moves along with that jar, and hopefully macerates the compounds into the product. And here's some pictures of some of the materials that we're using to do this stuff. So essentially jars come in a variety of sizes and materials. We use mainly these hardened stainless steel materials. They cost about £500 per set of jars, so they're not inexpensive. But you can make your own in an engineering workshop, and you can also buy them in different materials. So you can buy them in Teflon, agate, and zirconia, if you are concerned that the stainless steel and the metals in there might be leaching and having an impact on your reaction. So once you've got your materials loaded into the jars, you put them onto this mill, where you've got control of only two parameters really, and control of anything else is by indirectly controlling those two things. So these two knobs on the top control the time of milling and the frequency of milling. So that's one technique. And then in the middle here, we have a planetary mill. And in some of the earlier literature, so when Carsten Bohm was doing organocatalysis in the ball mill, some of his papers were using a planetary mill device, which works in a slightly different way and tends to give more shear and less impact into the reaction materials. But now I would say most of the literature, including in crystal engineering, is moving towards the standardized use of mixer mills. In order to scale this up, you can buy a bigger mill. There's always a bigger mill. You can mix paint and crush rocks in these large tumbling mills. But my fear and worry is that you can't accurately control temperature when you're trying to run reactions on this scale. So for our scale-up purposes, we've identified twin screw extrusion as a technique that we might want to use, which would allow us to keep the inventory of chemicals low at any one point in time as you run these materials continuously through a set of twin screws that also can apply mechanical forces. So with these two methods, the extrusion and the ball mill, you get a set of unique variables. And this, I think, was the fundamental puzzle that interested me when we started looking at this work. And so we started out by looking at the literature and trying to understand some of the parameters that you ought to bear in mind when you're doing this chemistry. And two things came through from the crystal engineering side, especially, that we were skeptical of at first. And so the first one is called liquid assisted grinding. And so this is the addition of a small amount of liquid to your otherwise solventless reaction, which to me felt like cheating, but it really does seem to be a legitimate effect. And I'll show you some examples of that. So sorry, the scale here is incorrect. There should be microliters per milligram. And so what you're doing, if you have solid materials and you get no reaction or no transformation, one thing you can do is add a small amount of these liquids, and you can screen various dielectric constants to see if it will switch on your reaction or alter the selectivity of your reaction. Conversely, if you have a different scenario where all of your materials are liquids and you're not getting a reaction, then you can add an inert solid additive called a grinding auxiliary. And here's some examples of those materials that have been used. And what this does is it hosts the liquids on the surface and allows much more effective transmission of energy into your reactants by having a host for that impact to take place on. But what we would probably advise after we've done quite a few of these things is to try your reaction, see what the rheology is, see what the yield and the outcome is, and then based on that, you might pick one of those two parameters to look at first. Okay, so we started by borrowing a mixer mill from Wretch in 2016, and we picked this fluorination reaction. There was no example of fluorination in the mechanochemistry literature at that time, and this was a very straightforward reaction where we would take select fluor as an electrophilic fluorinating agent. Its DSC trace says that it should be very much stable at room temperatures and up to about 50 or 60 degrees within a ball mill. It has a decay at 150 degrees. So we were quite happy to mill this material. And what we found in this project was that we could mono or difluorinate, depending on whether we used a liquid assisted grinding agent, which was acetonitrile, or if instead of adding the acetonitrile, we added base, then we could control going directly to the difluorinated product. And so that lag part, I think, interested me in its potential and puzzle. And one thing in the back of my mind at the start of all of this was whether we could scale up what we'd done. Could it actually make an impact on the world by being scalable? And at that time, Stuart James and Deborah Crawford were already exploring extrusion. They were experts. They are experts in this area. And so we went to Belfast to work with them on trying to translate our reaction in the mill to an extruder. And we found that we could do this relatively quickly. And within a 16-minute run, we could make 8 grams of product without any solvent in the reaction component and just a crystallization solvent in the purification component. And so I was quite still intrigued about this, but wanted to stretch the chemistry a little bit further. So we looked simultaneously at a few different catalytic reactions, one of which was the Buchwald-Hartwig coupling, which we managed to get to work, and it had a fairly broad substrate scope. we could run the reaction at fairly low catalyst loadings, 0.2 mol%. We only did one at that loading, everything else was 0.5 or 1 mol%. But what else we noticed was that we are not using a solvent, so we don't have to go to the rigor of drying a solvent. And we could also weigh all of the materials out on the bench and not do this under an inert atmosphere. Together with Louis Morel, we explored alternative activation modes for organocatalysis, so this NHC organocatalysis and this tertiary amine azamarita-Baylis-Hillman reaction. And both of these work quite effectively. Certainly the AZA-MBH reaction allows you to do this reaction within 3 hours rather than a 3-day process, which is a bonus. But probably one thing we did observe here is it doesn't do the asymmetric transformations of these very well. And I think that is because you don't have control, fine control of the temperature that you would do in a homogenized solvent system where the solvent is essentially functioning as a heat sink to control increase or decrease in temperature. So about this time, we tried to find a concept that we could latch onto to mechanochemistry, because one common question we were getting about this is, what is it good at doing? And so one idea that we had was that we could potentially activate zero-valent metals using this. So we started with zinc, which comes in a variety of different forms. And depending on the form, you're going to have your own local protocol to activate that zinc and get it to do your chemistry. So the idea was that we could mill the zinc in the presence of an alkyl or aryl halide, and irrespective of the form, we could get it to form an organozinc, which we could then open the jar and add a catalyst and a coupling partner and do the Negishi coupling. And this worked quite effectively. And we extended this to the Reformatsky and the Barbier transformations. And again, all of these seem to be form independent of the zinc. We could also use the zinc as a terminal reductant in nickel catalyzed cross electrophile couplings. And very much in the similar vein to Dan Vikes, we took inspiration from his work. Depending on the electrophiles that you're trying to combine in your coupling, you have to retune the catalyst system and the stoichiometry of the electrophiles that you're putting in. So here is a series of 3 papers where we have looked at that. Well, we tried to look at other metals as well. So manganese in the top left here, we were trying to make an organomanganese reagent and then explore what the possibilities are of this, these types of materials. But what we actually found was that we could reductively dimerize these arylidine malanates using manganese radical chemistry that seems to only switch on when you've got manganese at very fine particle sizes. And Professor Hajime Ito from Hokkaido University has since shown that you can make organomanganese reagents using these materials. So we found this unexpected reactivity of manganese by doing this. And then most recently, we looked at the Simmons-Smith cyclopropionation by zinc mediated processes, and we were able to cyclopropionate materials that you can't cyclopropionate in a solvent-based system, specifically some steroid derivatives. So we reviewed this area and highlighted the metals that had been used up until the time that we'd written the review, and then very quickly it went out of date. So Carsten Bohm, Hajime Ito, and Koji Kabuta, James Mack, and Early Liu from Newcastle have now added to this with calcium, sodium, and lithium. So you can mill all of these metals. I'm not convinced you should do this unless you've got a really good safety protocol in place and maybe a glove box available to you. But nonetheless, this seems to be unlocking reactivity and chemistry that isn't available without ball milling these metals. I think this has culminated actually this year in a collaboration very much led by Veronique Governor's team, where we were activating rocks essentially to generate a fluorinating agent. So historically, all fluorine comes from fluorspar, and you boil this up in sulfuric acid to make HF and then derivatize the HF to a number of fluorochemical intermediates. But by the use of ball milling, we could activate the fluorspar with a phosphate salt and generate this fluoromix species that is bench and shelf storable, and then use that to make a number of SF and CF bonds. So I mean, this story now has been going on for about 7 years in total. We've been working on this. We get a lot of frequently asked questions. So if people who are listening to this have any of these questions, that would probably be quite normal and a typical response. And I'm happy to try and cover any of those in any questions today. But what we got to at this point is we understood what happens when you do chemistry at a medium scale. So there is the potential to reduce the reaction time. You're at a much higher concentration. So that's not necessarily surprising. There is an unpredictable potential to enhance the selectivity of a reaction. And there's an unpredictable ability to turn reactions on that don't go in solution. But the fact they're unpredictable means they're not necessarily useful at the moment without a lot of prospecting work. But I think one thing that wasn't clear to us at the outset of this program was how many reactions can be made more robust, in that you don't need to have any solvent. So you don't have to dry the solvent, and you don't need an inert atmosphere. You can also get away with low catalyst loadings, and you're weighing everything on the bench. So I think this is an aspect that is coming through in the mechanic chemistry literature. And I've listed some articles here in terms of reviews on mechanic chemistry. So what I want to do now is tell you a little bit more details of a couple of projects that are unpublished on alternative scales. So one of the great aspects of mechanic chemistry that people often talk about is the ability to reduce the amount of solvent you're using. But my thoughts over the years have come to the conclusion that this only really applies when you're working on large scales where the volumes of solvent are huge. And so I tried to look at what that actually looks like. And so most chemical manufacture is done in solvent in these huge tanks that might sit in a multi-story building, and you're using gravity to feed from one reactor tank down to another reactor tank. And essentially you put in your starting materials, which are these blue and purple dots, and your solvent. And then at the end of the process, you fish out the green dots that you're interested in. Now in a manufacturing plant, your solvent will be coming in these standardized IBC tanks, which come in a range, smallest volume of 680 litres and up to 2,000 litres. And here is a warehouse where we're storing several of these with clean solvent ready to go into these reactions. And then we've got several of these that have now got waste materials in that need to be shipped out and disposed of. And so the extrusion offers a potential alternative to this where we don't necessarily need the solvent in the reaction. We will still need the solvent for the purification. So we're not necessarily changing anything about the purification by doing mechanic chemistry, but we can at least remove the solvent required for the reaction. And so I showed you one example of translating the fluorination to an extruder. And here I'll show you an example briefly of translating nickel catalyzed Suzuki coupling from a ball mill to an extruder. Now this was an approach here where we're milling our nickel catalyst with a base, a grinding auxiliary, and hexanol, which is required to generate the active catalyst species. And for this project, we had to design a unique heater, which had this particular heating profile. And we wanted to translate that to an extruder. So what we did first was essentially read and review the area on reactive extrusion. So there were about 10 to 15 papers on this topic. And then we set about having a go. So this is how we've set this process up. So in the middle of this diagram is the extruder, and we have 7 individually addressable temperature control units across the length of the barrel. So we can map the heating program we had in the ball mill onto the length of this extruder. We also have to configure the screw in a certain way, which we won't focus too much on here today. And then we have our solids all mixed up together, and they go into this solid feeder, and we pick a setting between 0 and 100 as to how fast that's going to feed into our twin screw. And then we've also got our hexanol liquid being fed by a syringe pump. The material extrudes out at the end, as you can see, is this kind of paste or gum. And within our first couple of runs, we managed to isolate 62% yield, which was a 14 grams of this nickel catalyzed product, which we were quite happy with, given that this was somewhere between an 8 and 12 minute residence time within that continuous extruder. So to try and develop more of an understanding, we looked at another reaction. So this is the direct amidation of esters. And we'd previously showed that you could do this using potassium tert-butoxide on quite a range of examples. And we wrote to the ACS Green Chemistry Institute to ask for funding to try to translate this from the mill to the extruder. And we were granted the funding, and we tried the reaction in the extruder. And then on our first effort, we can see that the reaction goes from right to left in this photo. And the nice thing about extrusion is you can stop the flow, you can take the lid off the top of these screws, and you can sample those screws whilst they're no longer reacting. And you can see we actually had quite a good result from our first go or two on this reaction. But if we wanted to change the substrates, or if we didn't have the good result, we didn't have a clue of what we would be doing to try to optimize this. So these were some of the questions we had following this successful reaction: is what would we do if this wasn't working so effectively? And so we spent about a year to try and understand this, doing various data collection and control experiments in the extruder. And what we found was that the feed rates of solids, including mixtures of different particle sizes, has an impact on how fast you're going to feed stuff into the extruder. Feeding of liquids needs some management in how you get the liquids in there to avoid clumping. How are you going to modulate the screw configuration in order to get the right mechanical energy into your system? And the most important thing I think we identified was that the rheology of the starting materials and the products has the biggest impact on success. And so this is what we did for a substrate scope that took into account rheology of the materials. So across the top, you'll see amines split into two sides with different melting points. And so the top left quadrant represents a scenario where we've got a liquid amine and a liquid ester. And then we've got two quadrants with liquid and solid combination, and a quadrant in the bottom right with two solids coming together. Now, all of these results I'm showing you here are done in the ball mill. And then we picked 4 of those to translate to the extruder. Now, as you may imagine, going to an extruder requires roughly 50 millimoles of material per data point that you want to collect. So our goal was to try to collect within less than 10 runs data points on those 4 different rheological scenarios. And so this is the table summarizing the optimal entry from those tables of entries of 10. Some had entries of 5 and some had entries of 12. And so the liquid-liquid combination requires a grinding auxiliary in the extruder and gives a 96% yield of the amide. And so you can see that these top 3 that all involve a liquid substrate need a grinding auxiliary included to give you the optimum result. And then the solid-solid one is actually better without the grinding auxiliary and gives you an 81% yield. So, I mean, overall, we were quite happy with the outcome from this study. And we managed to run an extrusion process for 7 hours, where we can now put all of the solid materials in. There's no liquids in this particular example. We've got a particular screw configuration, and then we collect the material over the 7 hours in batches as it's coming out, and we do a hot hexane filtration, and we can isolate 0.5 kilogram of this useless amide. So essentially, we're looking for interesting targets to apply this chemistry to. Okay, so this is the scale considerations we've got so far. So I think we can now have a good crack at translating from the medium scale to the large scale. But even at both of these, you still use quite a lot of material to find something out about your reaction because there is no solvent. And so really what we want to try to do is also go to the small scale to see if we can use this to give us data on either the medium or the large. And we've had these things here. These are holders for Eppendorfs. We've had those in the lab for probably 5 or 6 years. And it's always been my own skepticism that stopped us from having a go at this. I thought there wouldn't be enough energy in the ball to get this reaction to work, and I thought that the plastic of the Eppendorf didn't have a good enough hardness for transmission of that energy into the reaction centers. But I've managed to convince PhD student Sarah and visitor Federico to have a look at this, and I didn't tell them of my skepticism. And so the plan was to take several of our previous reactions and just reproduce those as a standard medium scale conditions, and then try to scale them down into the Eppendorfs, which are a 2 mil volume. And in order to scale them down, we're going to take the volume of the original medium-sized jar and divide it down to get to 2. And whatever that division factor is, we're then going to use that to divide down everything else in the reaction. So for fluorination, that was originally done in a 10 mil jar. And so scaling that down to an Eppendorf gives us a fifth of everything that's been loaded in, other than the ball that only comes in fixed diameters. And when we do this, we get very good translation from what was the medium scale down to this smaller 2 mil Eppendorf scale. And so, again, I was quite skeptical that this reaction must be quite easy, and maybe it's just induced by mixing. Maybe we should look at a range of other reactions. So Sarah was a very willing participant in this, and she went away and she identified that the Buchwald-Hartwig reaction and the amidation reaction worked. Federico looked at the formulation reaction from his own group, Andrea Puccetto in Cagliari in Sardinia. And he looked at the work of Hajime Ito, so piezoelectric borylation and a coumarin synthesis, as well as an isocyanate synthesis. And then Sarah's looked at nickel-catalyzed Suzuki's, carbon-sulfur cross-coupling, cross-electrophile coupling, and Barbier reactions of ketones and aldehydes. And in most of these cases, we get very good translation from the medium scale to the small scale. And the purple ones are coming from other labs around the world that are looking at mechanochemistry. Now, it's worth noting that these two reactions in red here that haven't worked very well, they're known to us to be temperature sensitive, in that we think the heat that you generate from grinding them in a larger jar with a heavier ball and a metal material is required. So we need some kind of thermal input, not just mechanical activation, to get these reactions to work. It's also worth highlighting that we can also do this zero-valent metal activation in this 2 mil Eppendorf sized jars. So that's where we are with this project now. We're trying to see how low we can go. There's quite a lot of things we could potentially do with this. So we could do small scale libraries, catalyst screening, reaction kinetics, prospecting for new reactivity. And there's also a lot of unanswered questions. And so we're thinking about going to high throughput experimentation devices. So as a summary, I would say that over this period, I've constantly been battling with my own preconceptions on mechanochemistry. One of them was that most reactions and catalytic processes need solvents to stabilize transition states. That doesn't appear to necessarily be true. Another one was that the residence time in an extruder wouldn't be long enough to get the job done. And that also doesn't necessarily seem to be true. And there wouldn't be enough kinetic energy in a 2 mil Eppendorf to get a broad range of reactions to go. But I think actually that there is. So the last thing to leave you with here is when to use mechanochemistry. And actually what I'm doing is when I don't think you should use it. So I don't think it's going to work well for Stephen Clark's complex total synthesis, and I'm sure he's not considering using mechanochemistry for that. I don't think it's good yet for controlling stereoselectivity. There might be one or two examples where it is, but maybe they don't require good control of temperature. And yeah, if you want good control of temperature, it's not effective. And then the last thought here is if we can translate one step of an active ingredient synthesis to replace it with an extrusion approach, the potential savings on solvent could be quite staggering. So with that, I would like to invite anyone who happens to be in London to come along and see the equipment we've got, and to thank all of my team members and collaborators for being willing participants in this research that we've been up to. So thank you very much for the invitation.
Super, Duncan. Great lecture. I still remember Karsten Bohm giving a talk probably 2004 in Dublin on ball milling, and it was certainly new to me then. And it's interesting to see how the field has progressed. And well done for all your contributions in mechanochemistry. So it's open for questions, and there's already one in the chat. I'll read it out from Syed Dubry. I'd already read this a little bit before I got to read it out. So there's lots of 3-letter acronyms. So if you don't know what they are, they are either. So hopefully you can follow it. If you had a reaction that required a LAG to provide high conversions in a ball miller, how would you translate this to a TSE question mark? And would you have to re-optimize away from using LAGs? So hopefully you understand what that all means.
Yes. So I think he's asking, if you have a reaction in a ball mill that needs a lag, how do you translate that to an extruder? So the answer there is that the lag that you're adding is always done as a microliters per milligram of total solids you've got in there. So that the translation is quite straightforward. Although we've only done one lag reaction in the extruder so far. And then the second part of the question.
Would you have to re-optimize away from using lags?
For the extruder, no, I don't think so. We found that anything that needs a lag in the mill also needs the lag in the extruder so far. But we've got very few data points on this. Like I would say, we've looked at 2 or 3 reactions, and the world in general has maybe got 20 papers on reactive extrusion. Yeah.
Okay, Amanda, you're up next.
Hi, yeah, when you were talking through the extrusion work, I noticed there was quite a lot of similarities with flow chemistry.
Yeah.
And I wondered if you could comment on like where you might use both, or what mechanochemistry would be better for, or flow chemistry.
Yeah, so I mean, it is flow chemistry. It is continuous processing, but it handles solids. So, and a big drawback of solution phase flow is that the arch nemesis is solids. So typically what you'll do in solution phase flow is high dilution to get around that problem, or sonication at T pieces where you might start to get particles building up. So I think they are very much complementary. And I think you could probably make a hybrid system where you'll use solvent-based flow and solid-based flow together in various permutations. But that I haven't seen that happen anywhere yet.
Cool, thanks.
Thanks, Amanda.
Great. Thanks, Amanda. I don't see any other questions coming through in the Q&A. And we're about 20 minutes behind time, so if you don't mind, Duncan, we might leave it at that.
Yeah,
super. Well done. Very interesting. Over back. Oh no, hold on. There is something up through Berit Olafson. Here we go. How do you work with risk assessment in mechanochemical reactions? Are there extra risks associated with these? And which parameters do you look for, if so? Thanks, Berit.
Yes, but very good question. This was the key to trying to get industry to work with mechanochemistry. And so we were guided by Syngenta on risk protocol, and we published an OPRD paper on how to assess the risk of a mechanochemical reaction. But the basic premise is to look for something called a plosophoric group. This is a material that has the potential to become an explosive. And there's a full list in that paper, but there's also several books that Syngenta knew about that I didn't, that will list plosophores.
Great. Amanda, if you can lower your hand, perfect. That makes it easier to follow what's going on. Now, Will, back over to you.
Brilliant, thanks, Pat. Thank you very much, Duncan. So over to Aylan now. So Aylan Lee is from Heriot Watt University in Edinburgh. Her slides are already showing. So Aylan, the floor is yours.
Thank you very much. Can everyone hear me all right?
Yes.
Yeah.
Yes, wonderful. So thanks very much for the intro, Will. And I'd just like to start by thanking the whole organizing committee for the opportunity to share my research today. So what I'd like to talk about today is the use of carboxylic acids as radical precursors, which can undergo decarboxylation reactions to form key radical species, which can then be trapped by various things. And here are some of the things we've trapped them with. But in today's We Talk, I'll really just concentrate on some brief highlights of our Minishi work that's trapping them with N-heterocycles. And then in the second half of the talk, I'll tell you in a bit more detail some recent work where we trap it with alkenes in what we call the Giza reaction. But before I move on to that, I thought I'll start by giving a brief outline of some of the kind of research we've been involved with. And since I started my independent career, much of our early work was all about developing transition metal catalyzed reactions, especially most of our work was with gold and a bit with palladium. And then we started moving into the field of developing new photocatalyzed reactions. So it's with great irony that what I'm going to tell you about today is all about metal-free and light-free reactions. So at least it started that way. And you shall see that we do bring the light reactions, light mediation back in where necessary. And nowadays we actually do compare both of them. And we're not biased against one or the other. I thought I'd maybe start off by telling a brief story about how on earth we started looking at this. And it actually starts with this project that I show you up here, where 10 years ago now, we developed a way to directly CH functionalize benzoquinones using palladium chemistry. It was not so well known at the time. But when we look at that kind of with a more critical eye, we realize that it's really only best for sp2 carbon functionalizations. So that R there was best with aryls and heteroaryls. So this project started because we asked ourselves a question, and that was, can we do a direct CH alkylation instead, meaning doing sp3 carbon functionalizations onto quinones for all the possible applications that might be. And to do this, we decided instead to look at some inspiration from a related reaction, which is the Minishi alkylation reaction. So I'll briefly introduce this reaction, although I think most of you are aware of it. But this is where they look at N-heterocyclic substrates, typically electron-poor substrates, pyridine-like substrates. And you can do direct CH functionalizations with radical precursors. So I've shown here Minishi's original conditions, and he used carboxylic acids as the radical precursor. And if we look at that today, this is considered a really good thing because they are inexpensive. There are loads of carboxylic acids out there, widely available, bench stable, so no special precautions, non-toxic, and also the initiation only extrudes carbon dioxide, which is a gas, bubbles away, so you don't have that issue of extra purification. Some people also try and say that you can get them from biomass, but that depends what the acid is. However, I think 50 years ago, they weren't so bothered about sustainability issues and trying to do late-stage chemistry. So there were a few limitations to the original, such as harsh conditions. They did heat it quite high. They used sulfuric acid and also expensive amounts of a non-sustainable and costly metal. So much of the modern research in the area, when we started looking at this, was kind of focused initially on making this reaction much milder so that you can apply it to late-stage functionalizations, which is what we want to do these days. And most of the groups at the time, their approach was to change the radical from carboxylic acid and activate it to something much more activated so that they could take the temperature all the way down to something milder. And typically, you'll see out there many examples of using redox active esters combined with photocatalysis, for example. And the oxidant is usually always still there, so that's still required. This, of course, introduces some other limitations, such as the availability of this. Now, you usually would need to have a few steps to make them for some of them, and also the poorer atom economy compared to carboxylic acids. So we instead decided to initially adapt Glorious's conditions, where he managed to show the use of carboxylic acids with photocatalysis in a Minishi with N heterocycles. So we first initially just said, can we just steal his conditions and try them on our quinones and see if that works? And it was a complete and utter disaster because quinones turned out to be light sensitive. So that wasn't very clever on our part. But this was what led us to discover what we discovered. So upon kind of optimizing and studying this reaction, we actually found that we could do the CH alkylation with carboxylic acids. And here was the surprise. We actually did not need any catalyst. We didn't need any metal. We didn't need any photocatalyst. We didn't need any light. And yet we were able to do the reaction under very mild conditions. And what was the really surprising thing was that this was not just for quinones. We were able to do this with your typical Minishi substrates, your electron-poor N heterocycles as well. And so we were wondering, why had we been throwing metals and shining lights and all these expensive metals at it when actually it probably wasn't necessary? So let me try and answer that question. We looked at various things, but in the end, we think it was actually quite a simple thing. The persulfate, which is always there in these, so there's always some oxidant, typically persulfate, it needs to break down to the sulfate radical anion, which is your key oxidant here. And typically, the silver or iridium photocatalyst or whatever in the light or very high temperatures, usually 100 degrees or above, is required for this breakdown. But this breakdown turns out to be solvent dependent. And if you change to just wet DMSO, this can actually go as low as 30 degrees. We were able to do this Minishi reaction. So all that's happening is we do a deprotonation. This both activates your heterocycle towards attack and forms the carboxylate, which is the species that undergoes the set oxidation, followed by decarboxylation to give you the key radical, which then adds to your activated heterocycle, and then you get your rearomatization. So we did the alkylations and acylations, but that's very well known and well studied. So what I want to talk about today for the rest of my talk is actually looking at direct amidations, because this is much less studied. And there are many potential targets out there that could be made this way. So just like some examples here of N-heterocycles with carboxyamides hanging off. And traditionally, you would have made this using a typical disconnection here, your conventional amide bond formation. But this requires you to access these pre-functionalized heterocycles that have an acid or an acid chloride hanging off them. And these typically are not commercially available. If they are, they're expensive, or it's several steps to try and access them. So our idea was to disconnect here instead and do a direct amidation using your N-heterocycles, which are much, much, much more readily available. And all you have to do is somehow generate carbamoyl radicals and do your Minishi type radical addition. And that should allow you to make libraries much faster and quicker. So to cut a very long story short again, we were able to do this using these oxamic acid radical precursors. So nowadays, a lot of them are readily available, but if not, you can also easily make it from the corresponding amine. And obviously, we used our metal and light-free methodology. You just have to optimize, get the concentration right. And as you can see here, we still have very mild reaction conditions, just 40 degrees here. And this is a typical substrate scope, so I won't go through it. I just want to point out that the scale up to a gram was a real doddle, because these are operationally very, very simple to do. We have cheap as chip reagents, nothing expensive there. This whole thing was done by an EuChemS project student. So just from milligram, we scale up to a gram. Typically, the reaction works absolutely fine. So with that, what we wanted to do next was to move away from these typical, relatively easy heterocycles you typically see in a Minishi substrate scope to heterocycles that were more challenging, that were maybe less studied. And I'd just give you some highlights of some of these. So one of the first more difficult substrates we looked at were the phenanthralines, because as you can imagine, there are many applications to these sorts of ligands once you've the dicarboxyamide. So this target, for example, was needed back in 2006 in a Fuldamer study, and originally they made this using typical traditional reactions, and it took them 11 steps from this commercially available starting material. Now, by developing our direct CH amidation methodology, so that's this reaction here, we cut this synthesis of this target down to 2 steps from this commercially available starting material. And I should say that's not our best yield. In our substrate scope, we're up to quantitative yields, and it's a column-free procedure. So the next thing we then decided to look at that was challenging were the purine family of bases and nucleosides, because it's the most widely occurring N-heterocycles in nature, and yet there were very, very few studies on Minishi, especially amidations on this. Typically, people would look at just caffeine in their substrate scope, but that's the easiest one to look at. All of the rest are much more challenging, and that's what we decided to look at. So again, I won't bore you with the substrate scope. I just want to say that we were successful in looking at this these classes of purine bases. And I just show you the summary of what we found from our substrate scope. So we summarized where the CH functionalization will go. So you'll see the direct amidation at those positions in green. And also we summarized which free NHs were tolerated and which NHs preferred to have a substituent on it for you to get a better yield. And as long as you follow these kind of guidelines, you should get a decent yield out of the reaction. So I'll just maybe show you a few highlights from our substrate scope. So on the 4 on the left here are xanthine-based molecules, including the the easy peasy caffeine, as you'll see, that's always the best yield, again, easily scaled up. But it also included xanthine type drug molecules that showed good functional group tolerance in late stage functionalizations. Our protected guanosine worked just as well. This is a drug that comes from an adenosine-based drug, and we have some guanine-based drugs. So it shows how this mild reaction is also good for late-stage functionalizations. And today, what we've done is to look at the next set of challenging classes, which are the 1,3-azoles, which appear one of the most important heterocycles in drug discovery, and yet there are very, very, very few studies, minutiae studies, doing direct amidations on this. So I don't have time to talk about that today. The manuscript's being written. We were successful in this, both with light and without, so hopefully that will come out sometime next year. I'd like to instead kind of talk about something else for the second half, but you will see how it's related in a minute, and that's our Giza amidation work. And I'll talk in a bit more detail about this publication, which came out earlier this year. I maybe first introduce what the Giza reaction is first of all. And it's the use of a radical precursor, which initiates to the radical that you want. So this is the key. It's basically a radical conjugate addition reaction onto Michael acceptors. You form this radical intermediate, and you can either undergo a hat process to form the product, a hydrogen atom transfer, a radical process, or you can reduce this through a set to the anion and then just pick up a proton through a normal ionic process. And you will see examples of both of these mechanisms later on in my talk. And unsurprising for something developed back in 1983, originally this used toxic reagents and harsh reaction conditions. So again, the more modern research has focused on achieving milder reaction conditions. And again, it's the resurgence of photocatalysis that really kind of brought this reaction back to the fore, and also generating radicals from more accessible starting materials. And as you can imagine from the title of my talks, starting from carboxylic acids is again considered a very good thing for all the reasons I've already mentioned. So let's talk a wee bit more about the R group here. So the Giza reactions were originally developed and very, very well studied for the Giza alkylations. And if you're interested in general, we recently published a review on direct decarboxylated Giza reactions. Acylations are okay, but what I'll just quickly show you is one of the most famous application of the Giza alkylation reaction, and that was by Macmillan back in 2018. So he utilized the photocatalytic Giza alkylation that he discovered 4 years prior to that and applied it to the bioconjugation of Michael acceptors onto the C termini of native peptides. So that's the acid there, so the decarboxylate, and it does the conjugate addition. So a beautiful application of this reaction. But what we were interested was not alkylations, because that's been studied to death. And what we were interested in was the amidation reaction instead, because this was much, much, much less well-known and well less studied than the alkylation. So what you want to do is to form a carbamoyl radical instead. And why? Because then you can form 1,4-difunctionalized compounds. And these particular ones are really not very easy to form by any other traditional method. And when we started this, there were only 2 seminal works, only 2 papers published in this area, both in 2020, both photocatalytic reactions. This first one here uses the Hanchester type radical precursor. So as you can imagine, that does have some atom economy implications. Also, they could only use very activated Michael acceptors, ones that had 2 withdrawing groups on it. This was somewhat addressed by the next paper, where they used carbamoyl chlorides and just 1 electron withdrawing group. But again, really quite simple Michael acceptors. And also these carbamoyl chlorides are carcinogenic, moisture sensitive, and rather toxic to make. And I don't know about you, but I'm a bit of a scaredy cat when it comes to using very toxic things like trifosgene. So it was very clear. These are really great seminal works because it shows that it can be done. But it's clear that there are 2 major limitations that we need to overcome before this work, this kind of reaction will be more widely accepted by the synthetic community. And the first one is the radical precursor. We really need to make this more user-friendly so that even people like me would be happy to use it. And secondly, we really need to expand the substrate scope, not just simple Michael acceptors, but towards the kind of thing you might want to start using in synthesis, such as cyclic enones, cyclic Michael acceptors, the kinds of, and that wasn't known. It's really quite challenging. So there were no examples of those. That's what we wanted to do. And I should also mention that earlier in the year, as we were writing our manuscript, Billy Kerr also addressed these issues by using metal oxamates, which clearly addresses the toxicity issue. So this was really nice to see. However, they are still slightly hygroscopic, and this time they had some slight limitation with the amide side, which only really worked with tertiary amides from the examples we saw. So in our approach, we wanted to use oxamic acids, because not only were they non-toxic, they're also bench stable. So operationally, they should be much more easy. And also, the most important thing we wanted to do was to get a more general substrate scope, both in terms of the amide, we want primary, secondary, and tertiary amides, but also in terms of the Michael acceptors. We really want to get those cyclic systems, things you want to use in synthesis, to work well. And it turned out to be a lot harder than we imagined. In order to get that general substrate scope, one development of reaction conditions was not enough. We needed to develop 3 different approaches to enable this more general substrate scope. So if you'll please bear with me, I will go through these 3 approaches. Now, the first approach is photocatalytic and called the reductive quenching cycle, and I'll use this logo to denote that later on. This is again completely copied from the typical cycle that you would use for Giza alkylation. So it's the exact conditions. All we've done is change alkyl carboxylic acids to oxamic acids. So you deprotonate, undergo a set and decarboxylation to form the radical, which then adds in a conjugate fashion. Now, this is where it will now differ from the next 2 slides. Your radical here gets reduced to the anion, which then picks up a proton. And because it's undergoing a reduction to regenerate your native photocatalyst, this is why it's called a reductive quenching cycle. Unfortunately, when we just tried these conditions on our model amidation, which was the primary amide, we got a really poor yield, 30-something%, and we saw a lot of this formamide, indicating that that radical itself could also undergo the reduction here. So clearly, we needed a different approach. So this was where we developed an oxidative method, and it's a no-brainer considering what you saw, that in our group, we will try initially at least the metal and light-free conditions. Now that first line is exactly the same as what we would have done for the Minishi. We decarboxylate to the radical, and this is mild because we use wet DMS. So in this case, it was 50 degrees. So we still needed some heat there to get this going. After conjugate addition, now we have no reductant because we're under oxidative conditions. So instead here, we have to add a hat source, so a hydrogen atom source, and we use terpenine to get to the product. And in our third conditions, we wanted to take the temperature down from 50 to room temperature. So we did that by adding a photocatalyst. So on the left, this is exactly the same as what you saw previously, but we've added a photocatalyst and light so that this initiation occurs through photocatalytic methods. And because this gets oxidized as we regenerate the photocatalyst in its native state, this is called the oxidative quenching cycle. And the persulfate is mainly here to just oxidize the catalyst. So let's summarize that. As I said, this takes it to room temperature. So our first conditions, reductive quenching cycle using this iridium catalyst. Second conditions, thermal using an oxidant. We change the base to collidine, and we have terpenine as the hat source. Third set of conditions, photocatalytic, exactly like B, but we add an iridium catalyst and shine a light to take the temperature down to room temperature. So let's see how these 3 conditions compare with our initial study of our 3 model substrates. As I've mentioned, the reductive conditions didn't look good initially, and we needed initially at least, it looked like the cheapest chips, easy to run reaction, conditions B, just the thermal one. seemed to work best. That's the box conditions there. But the situation started to look a bit different as we looked at the wider substrate scope. So let's look at the wider secondary substrate scope here. So these are the secondary amides. It looked initially like the oxidative conditions, either the thermal or the photocatalytic, seemed best for the secondary. So you'll see I've boxed some of the best and some others, they were kind of identical yield. And so we thought, okay, it looks like the oxidative conditions are the best, either B or C. But then we started to look at the tertiary amides, and we looked at these initially with just the two oxidative conditions. This is the product we want with the tertiary amide. What we saw as the major product had one of the alkyl groups fallen off. So that's the major there. How on earth did that form? So having thought about the mechanism, we think that the radical, upon conjugate addition, you form this key radical, and you want that to pick up a hydrogen from your hat source, your intramolecular hat source. But it can instead do intermolecular. Here it can instead do an intramolecular 1,5 hat. This forms a radical next to nitrogen, which is really susceptible to an oxidative set to your iminium, which can undergo hydrolysis to form that dealkylated product you see. I should first stress that this only happens with tertiary amides, because with the secondary, the alkyl groups kind of hanging off out of the way. So it seemed obvious that it was the oxidant that was the problem. So this was where we thought maybe the reductive quenching cycle, this is its chance to sing. And maybe we just need to switch to those conditions, and this would solve the problem. And that's exactly what we saw. This time, the photocatalytic reductive quenching cycle gave us a good yield of what we wanted and none at all of the dealkylated product. So with that, we were able to also look at tertiary amidation. So we needed different conditions to get this full substrate scope, as you saw. In terms of the Michael acceptor scope, so it's a no-brainer that the very activated ones with two withdrawing groups worked well. But what we were really pleased with was that we could now do these cyclic substrates, 5, 6, 7 membered rings, ketones, lactones, amides, substituents, esters, these things. These were not good substrates. They were really challenging substrates. So we're very pleased that we can now do it. And we can do it with kind of relatively simple acyclic Michael acceptors as well. So some of these here, but there's always a limit. Some of these simple acyclic acceptors, even though they worked in cyclic systems such as the ketones, the simple ones here didn't go quite as well. But nevertheless, we were very pleased with the cyclic systems. So this is my last result slide now. We just wanted to apply this to more complicated systems, such as amino acid-derived amidations with no racemization of the stereocenter. We could bring in natural product amines in the amidation. We could use natural product Michael acceptors. We could use bicyclic building blocks, so with good DR in this case. And there's always that one experiment too many, so we tried to combine the two complicated bits, and it kind of worked as an okay yield. Nevertheless, these are quite complicated structures, so we were pleased with that. So my time's up. I'll just conclude by saying that this was the first geyser that used oxalic acids, which are non-toxic and stable. We had to develop 3 complementary conditions in order to get the more general substrate scope. And it's the flexibility we needed there. So if you want to do this, try all 3 conditions. One of them will work for you. So I'd just like to thank all the co-workers, past and present, who worked on the topic that I talked about today, including our industrial collaborators, and also all the funders, again, past and present, who funded the work today. So thank you very much, and I'm happy to take questions.
Aylan, what a superb presentation. Very interesting stuff. And amidation makes another entry into today's work after having heard Duncan talk about it in mechanochemistry. You've given an alternative way of looking at amidation. And of course, making the amide bond, as you are well aware, is tricky, and the amidation reaction adds to all of that. So well done. I'll look for questions and answers. None coming through just yet from the attendees. Q&A. Any from the panelists?
A quick one, Pat.
Yep, sure will.
Thank you. Thanks a lot, Aylan. Really good. Are you able to comment on what's so special about DMSO? in reducing that redox potential that's central to almost everything.
Yeah, no, we don't know. So we looked at all sorts of things. So we couldn't see anything special about it, apart from the fact that what I didn't show was a very, very, very stark solvent screen. Nothing at 30 degrees, nothing. With every single solvent we tried, only DMSO works. If you heat it up in other solvents, it does start to work. So at 100 degrees and above. And also, if you use you should do light mediated. I didn't have time to talk about it today, but we've developed ways to use EDA to do these light mediated without catalyst. Again, that can work with light, but again, then you can use different solvents. So it does seem to be just a thermal thing. And there's a kind of hidden Russian journal somewhere that did state that these breakdowns are solvent dependent, and it's just better in these polyprotic solvents, and DMSO is just the best. So it just kind of tips the scale. And the concentration is crucial too. So all the previous work that shown light that we're using photocatalysis, their controls were true, because you had to find the sweet spot of concentration for this to work without the catalyst. And that's the crucial thing.
Thank you, Alan.
Thanks, Alan. So perhaps in the interest of time, if you don't mind, we might move on to Ed, who, oh, hold on, there's one here coming through in the Q&A. Adam West, on the same lines you mentioned about water wet DMSO, why do you think this is significant? Thanks.
Yes, so firstly, it's very easy to use wet DMSO. It's just an open bottle. And we compared it with the dry. It still works, but the yields were not as good. So we think it's just a solubility issue, because our ammonium persulfate just dissolves a bit better the more water there is. And then there's again a sweet spot. Too much water and the yield starts to drop again. And also we looked at the counter ion in the persulfate. Again, ammonium was the best. Again, I think just a solubility issue. At least that's our hunch. And it's about 4.3% by weight water is the kind of bottle that seems to give us good yields. But in general, an open wet bottle will work fine.
Great. Thanks, Alan. Oh, back over to you again, Will.
Brilliant. Thanks, Pat. Okay, Alan, so if you can stop sharing your slides, please.
Okay, how do I do that? Stop share.
Brilliant. So, and now we have, last but by no means least, Ed Tate from Imperial College London. Ed's slides have appeared miraculously on cue. So, Ed, thank you very much for joining us. The floor is yours. Looking forward to it a lot.
Yeah, thanks, Will. Thanks very much for the invitation. My apologies, I'm in the middle of quite a busy part of Athens, it seems. And I'm sorry if we get any road noise. Hopefully we won't. So yeah, thanks very much. I'm going to tell you today a bit about our work on chemical biology and protein modification. So this is really about how we're using different sorts of organic chemistry, chemical probes in the context of modulating or controlling how proteins are modified, and particularly in cells. So just to give you a quick overview of the kinds of things that we are doing in the lab, we work a lot with photoactivatable drug molecules, for example. So you can see the diazurine here in the alkyne tag. If we're looking at target engagement of PARPs or other targets inside cells, also photocross-linkable peptides. And we also work with activity-based probes. I'll say a little bit more about that today, but that react covalently with the active site of enzymes. An example here shown for various types of secreted proteases that are important in cancer. And we also work a bit with antibody drug conjugates, so conjugation, organic chemistry conjugations to proteins, and photoswitchable protacs, which I'll say a bit more about today. So I'm going to start by just introducing the ubiquitin proteasome system for those of you not familiar with it. Very important system in cells for controlling protein stability and protein degradation. So this is a process with multiple steps that I won't go into detail, but it involves the addition of a small protein called ubiquitin. This is about an 8,000 Dalton protein. Ubiquitin is quite small, which gets added to substrate proteins through a cascade of what we call ubiquitin ligases, so E1, E2, and then ultimately E3 ligases that recruit substrate proteins and allow a ubiquitin to be transferred to an amine group, so on a lysine residue. That's the signal to then build up a chain of these ubiquitins, which can form different sorts of branch chains, as I'll say in a moment. And that can result in many cases in the degradation of that protein. So it gets recruited to a sort of proteasome, the proteasome, which is a proteolytic machinery in the cell that specifically targets these ubiquitinated proteins for degradation. And that turns the protein back into fragments and recycles the ubiquitin. But there are also these enzymes called DUBs, or deubiquitinating enzymes, that can reduce the chain length dynamically. So at the same time as this system is trying to extend the chain and degrade the protein, these DUBs are taking those ubiquitins back off, and effectively that you get an equilibrium of addition and removal that allows the cell to control very finely the rate of degradation of these different proteins in the cell. And because proteins rely on cells for all of their function, this is fundamentally important to pretty much everything in the cell. This is the protein ubiquitin shown in 3D here. Each of the lysines is shown in a different color. And actually, though I won't go into that today, there's different functions for ubiquitination at these different positions. So depending on where different ubiquitin chains are attached to these proteins, you get different results. So K48, for example, results in degradation, but some others can result in different signaling pathways. So it does more than just degradation in the cell. And therefore, these proteins, these DUBs, these enzymes down here, which are actually potentially quite druggable, are very important in regulating the system, because they're the proteins that they're the enzymes that tend to stabilize substrates. So if you break down the ubiquitin chain, you tend to increase the stability of the protein rather than causing it to be degraded. And one of the challenges in this field is a lack of really good small molecule probes for these proteins. So at the moment, people in the field take the whole of the ubiquitin protein. So the ubiquitin protein is about 8,000 Dalton, as I mentioned, and turn it into a chemical probe. So they chemically modify the ubiquitin protein with a chemical trap that allows that protein to react, the ubiquitin protein to react covalently with a DUB. And it does so by binding into the DUB active site, because the DUB recognizes the ubiquitin. And then there's a cysteine in the DUB active site, which reacts covalently with a warhead that's been attached to the ubiquitin. So you actually have to synthesize these ubiquitin probes. Often they're actually synthesized by peptide synthesis. You synthesize the entire ubiquitin molecule, which is over 70 residues long. It's a massive piece of synthesis you've got to do in order to be able to chemically modify it in additional ways. So this is a pretty powerful tool, and actually most of the field uses this. This is the tool that's generally used, but it's limited in the sense it can't go inside the cell. So it's an entire protein. You can't add it to any kind of living system. These ubiquitin probes are too big to get inside cells, and it doesn't really profile drug target engagement. It can't profile drug target engagement in cells. So what we really need for that is a small molecule probe that does the same thing as this entire protein, but compacted down into a really small molecule, the drug-like molecule. And then we'll be able to get into intact cells and probe how these enzymes work inside real living systems. We need to get down to the sort of classical drug-like size, sort of 400 Dalton or something like this. And if they worked as well as the ubiquitin probes, that would be about 20 times more efficient, right? If they're as good as a ubiquitin probe, then this small molecule represents much more efficient chemistry, if you like. So the interaction is much more efficient if you can achieve it in such a small size. So really what we're trying to do is take down this big guy, this enormous ubiquitin probe, and replace it with something that's much neater, much smaller, small molecules. But this is not trivial, because inhibitors for these enzymes are difficult to develop, as it turns out, and also probes that are hard to develop. So it's a real challenge to discover and develop these probes. The reason for that is this shows a DUB on the left here in kind of salmon. This is the DUB enzyme bound to ubiquitin in this sort of space filling model, and you can see that ubiquitin binds to a big surface on the surface of the DUB, so it engages a lot of residues and changes the active site geometry. This is the active site down here. This is the cysteine that does the reaction, the proteolysis reaction. And the C-terminus of the ubiquitin protein really enters the site down here and becomes the substrate for the protease. But it really organizes this active site when it binds. So there's interactions in these loops. You can see all these loops that it engages, which change the geometry to a significant extent. And when the ubiquitin is not bound, which is the pink line here, this histidine, for example, is not correctly aligned. So the actual protease activity of the protein is reduced or negligible unless it's bound to ubiquitin. And that's the reason why it's really hard to develop small molecules for this protein, because you can't easily mimic what ubiquitin does to a DUB to activate it with a small molecule, because it doesn't make all of these additional interactions. So the whole field has taken a long time to discover molecules that can do this. Working with Mission Therapeutics, which is a biotech out in Cambridge, we discovered this class of molecules. They contain a cyanoamine motif, and it turns out the cyanoamine is the trick here. So this is a reactive motif. The cysteine of the active site can attack the cyano group and obviously form a relatively stable linkage. So a covalent bond is made to this molecule. And this warhead seems to be the sweet spot, or the correct reactivity and the correct geometry to be able to engage DUBs even when they're not bound to ubiquitin. So this is a small molecule compound. It inhibits one particular dub called EuCH01 with pretty good affinity, so 90 nanomolar IC50. And we changed this into an activity-based probe by putting an alkyne, adding an alkyne onto this structure in a position that didn't change the activity, so it remains very potent for EuCH01, but it provides us with a handle for doing click chemistry and subsequent analysis. Biochemically, this compound retains really good selectivity across the dubome, so across all the different dubs. It retains good biochemical selectivity for EuCH01 and doesn't touch too many of the others. So when we do one of these experiments, we treat cells with one of these probes. So this is the reactive warhead that's going to form a covalent linkage to the dub. We add it to an intact cell, so living cells in a plate. And the alkyne is the handle that's going to allow us to identify what this molecule binds to. So we allow that molecule to engage its targets inside the cell, whatever they may be. And then we use click chemistry to pull out those targets after we lyse the cells. And here we're using an azide with a biotin and a tamer. So a fluorescent dye to image these things and a biotin to allow us to enrich them. This is the power of click chemistry, of course, that we can do this reaction in an incredibly complex system. And when we look on a gel, so for those of you not familiar with gels, each of these bands represents a protein, in this case, that's labeled by the compound because it's picked up the alkyne tag and has become fluorescent. And you can see here, this is the band for EuCH01. So at concentrations down into the low nanomolar range, this probe really selectively targets EuCH01, not just in recombinantly with biochemical assays, but also directly inside intact cells. Which was the first ever probe, in fact, for this kind of approach for a dub. And with proteomics, we can pull down these labeled proteins and analyze them, discover what is labeled by using proteomics, basically identify all the proteins on this gel. And indeed, EuCH01 is by far the main one, and most of the other dubs are not engaged. For those of you less familiar with proteomics, this is called a volcano plot. It just shows the selectivity across the whole of the proteome. So in green are all the dubs, and you can see that EuCH01 is by far the major one. And indeed, we can demonstrate that we can pull down this protein by other methods, by Western blots, and show that EuCH01 is indeed the main target, and the off targets are pretty negligible. So this is the first example that you can really engage a dub selectively inside the cell using a small molecule activity-based probe instead of this enormous ubiquitin protein. We can show by mass spec, for example, that we modify the protein just once with our probes. And this is because the active site is the only cysteine that's labeled. Other cysteines in the protein are not labeled, so it's very selective. And it requires the active site cysteine to do that. So if we remove the cysteine from the active site, the protein doesn't get labeled at all. And we also see the kind of pharmacology that we expect from this kind of molecule. So our probes also recapitulate what we expect from EuCH01 inhibitors, which turn out to be anti-fibrotic agents. So they tend to reduce the production of fibrotic proteins in fibroblasts. So this is quite a big step forward. We managed to make the first small molecule probe that could basically mimic this entire ubiquitin protein, but it only labels one protein, it only labels EuCH01. And what you really want to be able to do is label all of the dubs very selectively at the same time, which is also a very powerful way of determining their activity inside the cell. So if a dub reacts with your probe, it's because it's become active. And then you can understand how the dubs are activated and regulated inside the cell. So we also want probes that can target lots of dubs within the dubome, but without causing cellular toxicity and in a very selective way. Crystal structures show how these kinds of compounds work. So there's actually a covalent bond down here to the active site cysteine in this crystal structure, and actually it mimics the C-terminus of ubiquitin very nicely. So these compounds actually thread into the active site, which is where the ubiquitin C-terminus would normally go, and make different interactions, not the same ones. It's not mimetic in terms of the hydrogen bonds that it makes, but in terms of the shape and the geometry of the interaction is very similar, and it actually manages to organize that histidine I mentioned before. So this active site is well organized with these small molecules. So I think we don't fully understand how this is achieved in terms of the exact bonding that occurs, but it does seem to be a very effective warhead, so a very effective chemical warhead for doing this. That's been taken up, I guess, by the entire field. So there's many patents now published that use cyanoamines as the warhead. Over 2,000 examples in the patent literature, relatively few though in the academic literature, which target a range of different dubs. So it seems like this chemical warhead can target many different types of dubs, not just EuCH01, but in principle, you can expand it to target many others. And we took this principle as a starting point for developing a broad spectrum probe that we could put into cells and that would react with all of the dubs in the cell at the same time and allow us to read out the activity of all of those dubs just in one experiment. And we scanned through many different warheads and did proteomics on all of them, and we identified once again the cyanopyrrolidine, so cyanoamine or cyanoprolidine in this case, as being by far the most effective warhead. It picks up far more dubs than any of the other things we tried. We tried many others. I mean, for those of you who work on covalent inhibitors, you'll recognize many of these warheads, Michael acceptors and so forth. But really, it's cyanoamines that have this special character that goes to the active site. And when we put this into different cell lines, we can see really amazing dub coverage. So we're targeting all of these different dubs. Each of these represents a different dub inside the cell that we're targeting with the probe and then pulling out and then identifying by proteomics. So this really is a broad spectrum molecule, and it's all furthermore not toxic. And we can use it to do experiments to show, for example, target engagement by drugs. So this is a drug that's used against USP30, which is another dub. We can pull down USP30 using our broad spectrum probe, and then we can compete against that interaction by adding the inhibitor first. We add the inhibitor first, and then we add the probe, and that can outcompete the pull down of USP30 in this case. So we can effectively use this probe for the first time to look at dub activity across the dubome inside intact cells, and also look at drug target engagement inside those cells as well. So we've used this in quite a lot of different contexts. So we can now, it's not toxic, it can be applied in live cell imaging and live cell experiments. It can monitor then the activity of these proteins in real physiological contexts, and it's active site directed. And we've used this, for example, to understand how activity of dubs is regulated differently than their abundance. So it's not just how much dub is there, it's really how much activity you have from that dub. And this just shows one of those experiments where we measured the abundance on this axis. So the change in abundance in response to switching on an oncogene, so a gene that causes cancer. When that gene is switched on, it changes the abundance of dubs, but it changes their activity a lot more. And it changes their activity very differently than it changes their abundance. So there are additional layers of regulation that are not just about how much dub is there, but really how active it is. And you can think then about using those activities as starting points to identify drug targets in this context, right? You could say if a dub is active in a cancer, it's because it's a more important, potentially it's doing something important, and we can potentially go after it, but in drug discovery. So I think it's the start of a new approach to understanding how this whole system works. I'm going to conclude by saying a few words about our work on PROTACs. So this is kind of the flip side of instead of inducing stabilization, this is inducing degradation. PROTACs were first reported in 1999 in a patent. It's taken about 20 years for them to get finally to the clinic, but what these molecules do is they're very clever. They assemble protein complexes inside cells that were not there before. So if you have an E3 ligase, that's the enzyme that ubiquitinates protein substrates, and you have a protein of interest that you want to degrade, for example, that you want to actively ubiquitinate. And these proteins don't normally interact with each other. So normally the E3 ligase will not see the protein of interest, and it has no affinity for it, and it won't degrade it. PROTACs allow those proteins to form a novel interaction. So the PROTAC grabs hold of the E3 ligase, it grabs hold of the protein of interest, and it brings them into proximity. And it's the proximity, the local proximity of these proteins that allows the ubiquity to be transferred to the protein of interest. So you're effectively assembling a new protein complex using a small molecule, which is really a radical concept, and why it's really taken drug discovery by storm. Everybody is now, of course, working on degraders and molecular glues and similar kinds of modalities. But by adding just this pharmacological agent, just this drug to the cell, you can induce the ubiquitination of your protein of interest, sometimes very selectively, and then cause it to be degraded. So you can target things that are also not enzymes. You don't need to have an enzyme activity. You can target proteins that are just involved in, for example, scaffolding other proteins or anything you would like. Really. So it's has many pros. It's catalytic because it uses an enzyme, the E3 enzyme, to kind of cycle through. So you can recycle the PROTAC and use it again. So one PROTAC can, in principle, degrade many targets, and it degrades targets instead of inhibiting them, which is a really radically different way of doing drug discovery. But it's challenging to develop the linkers to actually make PROTACs that work and have good kind of drug properties is actually quite difficult, because basically they're two molecules joined together, so they're often twice the size of what a drug would normally be. So they can be quite challenging to develop. In my lab, we've been trying to figure out how you control the activity of these molecules to a further degree. So can you switch them on and off, for example, using light or other physiological responses, and can you target them? So can you find ways to target one of these very novel molecules to a specific tissue and achieve target degradation just in a particular tissue type? For example, this is an example of one of our photoactivated PROTACs. So here we're adding a photo cage to a PROTAC. This is the PROTAC here. JQ1 is the molecule that binds to the protein of interest. So this is an inhibitor of bromodomain proteins, so a particular class of proteins in the cell. It binds to them and inhibits them. To that is attached a linker, a simple PEG linker, to an E3 ligase ligand, and this is the thing that will recruit the E3 ligase to the protein of interest. So if we put this molecule in cells, in principle, the E3 ligase will be recruited to the bromodomain via the JQ1 molecule. But we've added this photocage to this hydroxyl that you can see here, and this hydroxyl is critical for binding to the E3 ligase. That's this hydroxyl here. When this hydroxyl is masked by the photocage, it can't bind to the E3 ligase, and it's effectively switched off. So we can basically keep this PROTAC switched off until we want to activate it using UV light by uncaging the photocage. How does that work in practice? So this is what the normal PROTAC does. It degrades very beautifully BRD4 in cells. So we add it to cells and then measure the amount of degradation. This thing works very beautifully. With this photocage in place, you can see the minus lanes here. The protein's not degraded at all. But when we flash it with UV light, you can see what happens. We switch on the PROTAC activity, and now in a light responsive way, we can initiate the degradation of BRD4 just in response to shining light on our cells in this case. And it also works very rapidly. So it works as quickly. It doesn't take any additional time to work. It works just as quickly as the uncaged PROTAC. So as soon as we uncage it, it immediately has its full effect inside the cell. And in fact, inhibition is very different than degradation, as I mentioned before. So inhibition of BRD4 just causes cells to sort of stop dividing. It doesn't necessarily kill them. So cancer cells tend to sort of stop working. And that's what we see with the caged PROTAC as well, because this protein of interest ligand is still available. The JQ1 part, this part, the green part, can also still inhibit the target. So it still has its sort of anti-proliferative effect. The cells don't divide. But when you uncage it, you switch on a very strong cytotoxic effect. So if we remove BRD4 altogether by degradation, then the cells feel it pretty badly, and then you see cell death. So you can get very different pharmacological outcomes from inhibition versus degradation, and now you can also control it using light. And we can see this also in cells. So in the absence of adding UV light, in the absence of shining UV light, we don't get any degradation of proteins also under the microscope. And when we add UV light to this system, we flash certain cells. So in a very specific way, you can direct your degradation activity to certain cells in your system by shining a UV light laser just on those cells, and you can induce degradation in a spatio-temporally controlled way. So also in terms of space as well as time, you can choose when degradation occurs. We've been investigating how we use photo switching as well. So photo switching in the linker. So here we've changed the linker. Instead of just having a PEG, we have a diazo group which can be switched between the cis and the trans. And you can imagine here changing the geometry of the linker could also change the activity of the PROTAC. So here the idea is you switch using UV light between the trans and the cis linker, and it changes the geometry of the molecule, and then we'll change the activity of the PROTAC. So maybe we get degradation with one and not with the other. So we can switch then degradation on and off if you like. We did this using a promiscuous kinase inhibitor that binds to many different kinases. One of the really nice things about PROTACs is it can turn a very promiscuous inhibitor that would be quite toxic into something that's very selective. So the addition of this need for degradation can actually change very much the selectivity. So the selectivity of degradation doesn't always match the selectivity of inhibition. And we can switch this molecule very nicely on and off. It's very easy to switch between the E and the Z. This is a collaboration we did with Matt Fuchs's lab. This pyrazole is something that he invented in his group. It's a very efficient photo switcher. It has a very long half-life in the cis form. In the less stable form, it has a half-life of some days usually, and we can switch it very, very readily. And indeed, when we're in the trans form, so this is the trans form of the diazo group, we see degradation very selective of certain kinases. All the kinases here are in blue. We only see degradation of a very select few. And when we switch it to the cis form here, so the cis diazo, we switch off the activity altogether. So we can effectively switch inside an entire family of proteins, the kinases. We can switch on degradation of a specific subset of them or switch it off in response to different wavelengths of UV light. We did some modeling with the Kozakov group at Stony Brook to show that indeed it's the E form, the trans form of the diazo group that forms the better complexes. And it really seems to be that allows it to recruit the E3 ligase. It's the geometry of the linker which allows that complex to form. And when you switch it to the cis form, it no longer binds correctly. There's a challenge with using light to do pharmacology in that most light obviously doesn't penetrate very far into the body. So actually using UV light to do drug activation is extremely difficult. You can't really use UV light or any kind of light really to do this, except on the skin, of course. But to get into internal organs and do this internally is very hard. So we've started down this route. Maybe some of you may know that when you treat a patient with a radionuclide, it can release things like positrons, so very, very energetic particles that are the therapeutic or imaging agent that can cause the cancer cells to die, mostly by damaging DNA. So very, very energetic particles. But they're released close to the speed of light, and in their media, when they're released inside the body, they're released at much higher than the speed of light in that media. So when they hit tissue, they have to slow down massively. So the deceleration that occurs there actually releases UV light, and it does so in a way that's kind of internal to the organ. So if you can deliver these radionuclides to organs, when they release their radiation, when those particles slow down very rapidly, they release UV light, and it's called Cherenkov radiation. It's the reason that nuclear reactors glow blue. So when we use fluorine-18, which is not a very potent inducer of the Cherenkov effect, we don't see any uncaging of the molecule. It just remains caged in this case. But when we use EuChemS that produces 57 protons per decay, 57 UV light protons per decay that it undertakes, then we can uncage using this radionuclide. So we think if we can deliver the radionuclide into the solid tumor, of which there are already antibodies that can do this, and then add a PROTAC or a caged PROTAC on top, we can release in a very localized way using UV light just within the organ and induce degradation in this sense. So this is a kind of ongoing ambition that we would like to try to do. Finally, we've connected PROTACs to antibodies as well. So you'll be aware that antibodies recognize specific antigens on the surface of cells. So in the absence of an antigen displayed on the surface of the cell, nothing will happen with these molecules. But if the antigen is expressed on the surface of the cell, it'll engage the antibody, which is carrying the PROTAC, and that PROTAC will be carried inside the cell only on cells which express the antigen, released inside the cell in theory, and then it will cause degradation. So you could target degradation to a specific tumor or specific tissue by virtue of binding to an antigen. And this is a big area of current interest in pharma, of course. And we did this in collaboration with Jamie Baker's lab at UCL. So you can reduce the disulfides using TSEP of an antibody and then rebridge them using these beautiful bromomylamides that Jamie's developed. And in this case, using another type of click chemistry, so strain-promoted click chemistry, we now tag these antibodies basically with a strained alkyne. Then we can do the same trick as we did before. We effectively cage that alcohol, but now with a linker to an azide. And the azide can obviously undergo copper-free click chemistry with the strained alkyne. So we can very easily and rapidly form these conjugates between the antibody and the PROTAC. And that's what's shown here. So we used an anti-HER2 antibody connected through the ADC linker. This is the strain-promoted click chemistry here, through this hydroxyl onto the E3 ligase ligand. So this remains inactive and unable to bind to the E3 ligase until it's released here. And then we've got the same ligand as I showed before. So this is the linkage. This ester is hydrolyzed when the antibody is internalized, and inside the cell, esterases will cleave that linkage and release the PROTAC. It's stable outside the cell, so just kind of in media, it doesn't get degraded. And indeed, in a HER2 negative cell, so a cell that doesn't express the antigen on the surface, you don't see any degradation. So it just sits there and nothing happens because the antibody is not internalizing and delivering the PROTAC. But in a HER2 positive context, so here you see beautiful degradation. So 100 nanomolar of our antibody PROTAC conjugate, only in a HER2 positive context does this get internalized, and then degradation is targeted specifically to those cells which express the antigen. And this will be a way of targeting degradation to specific tumors, for example. So I'd like to end there by thanking my lab for their many contributions to this work, our funders, the various alumni who've worked on these projects, and thank you for your very kind attention. Thanks.
Ed, thanks very much. What a super talk, and what a great finish to the list of 7 speakers we've had this morning. And well done for dealing with the background police or ambulance noises that were going on. So
there's something going on in Athens, isn't it?
Okay, now it's open for questions and answers from, or questions, I should say, from attendees or panelists. So maybe in the absence of anyone else, maybe Ed, I'll ask you the warhead, the sort of active pyrrolidine nitrile. That's an interesting finding. It's curious how it's that motif has been unrecognized, and now all of a sudden it seems to be a huge opportunity in drug discovery. Does it have to be a pyrrolidine nitrile? Can any other? Why doesn't it normally work with a carbon-based nitrile? Is there something specific about the fact that it's a nitrogen to cyano linkage?
Yeah, there does seem to be something about that nitrogen. I mean, it doesn't have to be a pyrrolidine. Yep. There are plenty of other ring sizes that work just as well. Mostly cycles actually, rather than linear chains, possibly because of the geometry of the active site. So yeah, what is it? And actually, you can use quite strained rings, so 4-member rings, for example, as azetidines and so forth. So you can use quite strained rings with amines in them. So I think It's an interesting question how that's changing the reactivity of the cyano group, right? And whether it's but if you don't have an amine, so it's just a straight cyano group, you don't see any interaction at all.
Yeah.
Sometimes if you have the ubiquitin protein present, you can get away with putting a cyano group on the terminus, or even an alkyne. So very normally not activated species can work if you highly activate the DUB by also binding an entire protein to it. But for these small molecule probes, it seems like there's something quite special about the cyanoamines. We don't have many structures of these molecules bound to DUBs, right? So there's a limit to what we know currently about how these molecules actually work on DUBs. They're also labile, so they can also be hydrolyzed later on. So they have that liability as well. So I think the field is kind of slowly coming to grips with how to use these warheads effectively. And the first drugs are entering clinical trials, so it's quite promising.
Great. We have a question coming in from Daniel Welligan. You showed it is the trans-diazo linker that is the active form of the PROTAC using modeling. Could you prove it by synthesizing the cis and transalkene linker analogs and seeing which is active?
Yeah, we could do. As it turns out, the alkene doesn't actually adopt the same geometry as the diazo does. So it's not trivial to accurately mimic the diazo. In terms of the orbital interactions involved, it's not exactly the same geometry, but yes, in principle you could, right? I think it's also an interesting thing to do, and something we did consider doing, but in this particular project we didn't. Yeah.
Okay.
It's a good idea.
So thanks, Daniel, for that. Any other questions coming through from panelists? I think after 4.5 hours of chemistry,
no, I can imagine,
are wilting, and maybe lunch beckons. There could be that as well. So it doesn't seem like there's any other queries, so we'll leave it at that, if that's okay. So just to wrap up, maybe Will, you can say a few comments, and then I'll wrap up on behalf of EuChemS, if that's all right.
Yeah, thanks, Pat. Not too much to say from me, really, other than to thank all the speakers for contributions today. Really 7 excellent talks and 7 completely different talks, which is exactly what we wanted to see, really, in terms of displaying the diversity of science that organic chemistry is these days, both in the UK and around the world. So thank you all for your contributions, and back to you, Pat.
Great, thanks, Will. So again, begin by thanking Will, my colleague on the EuChemS Division of Organic Chemistry, for organising this along with Louis and Joelle from the Royal Society of Chemistry, and we got a good background on the importance of chemistry to the UK economy. £54 billion of exports. That should fund a lot of PhD studentships. Good luck with that. And then, of course, the chemical and pharma industry being the second largest manufacturing industry in the UK, that's no surprise either. And I liked your quote about chemistry is the central science and organic chemistry is the central chemistry. So that's I'll use that one line at some stage. Well done. And I suppose as an external person to the UK, I've always known the strength of organic chemistry across the UK for traditionally over many years at this stage, and it's great to see all the way from Perkin and to Barton and all those legends of organic chemistry to the more recent people who gave talks today. So really fantastic representatives of the strength of UK chemistry, starting off with Steve, and I learned lots. He's had to go, unfortunately, lots about mechanical stereochemistry, axial and planar chirality in these systems that I didn't know very much about. So that was really an interesting talk, very beautifully presented, as all people in supermolecular chemistry seem to do. They seem to have lots of time in their hand for colors. So that was really a great talk from Steve. Then we moved over to Amanda, talked about artificial enzymes, and in particular for metalloproteins, and using non-canonical amino acids, particularly one that are BIPI-derived systems, and lots of applications of those systems in things like asymmetric Friedel-Crafts reactions and ruthenium catalyzed transfer hydrogenations. Then we moved over to Stephen Clark, who talked about complex fused polycyclic ether marine natural product synthesis, and indeed very complex stuff. But when you focus in on all the synthetic steps, ring closing metathesis seems still to be a very important component of what's going on there. And as someone who works in palladium catalyzed decarboxylative asymmetric alkylations myself, which we often called DAAA. It's nice to see that being one of the key steps in your synthesis and how all that worked. So well done on all of that. Our fourth speaker then was Rebecca Mellon. Again, a radical approach to frustrated Lewis pairs, I should say, and using that methodology for making not just carbon-carbon bonds, but more interestingly of recent note, the carbon-sulfur bonds. So that's interesting again, and ring closing metathesis, post-synthetic modifications of all of our work as well. Very interesting stuff. Then all the way to ball milling and Duncan Brown and mechanochemistry. So again, learned lots of that, the use of zero-valent metals in synthesis. I'd known about Veronique Gouverneur's work on mechanochemistry and how that's really making fluorine chemistry a lot more amenable and good for potential patients in the future. Lots of nickel catalyzed Suzuki-Miura couplings, amidation of esters. We had a lot more amidation then when we turned to Ailan Lee, who talked about decarboxylation in both the Minsky reaction, but also the Giese reaction. I liked some of her phraseology, cheap as chips. Not quite sure how transferable that particular statement is across Europe. I get it. I'm sure people in the UK get it. But people further east might find that phrase a little bit hard to get. Even though she also talked about hidden Russian journals. So if you go far east enough, you will find some hidden Russian journals as well. So interesting terminology, but fantastic chemistry again from Ailan Lee. And then we finished up with Ed, who's in Greece, I know, and dealing with background noise. He did particularly well. And it's interesting, click chemistry was one of the key sort of steps that sort of went through his work as well. And as someone working in Dublin, it was quite hard to hear about dubs, because that's what people abbreviate, people who come from Dublin and people who support Dublin football and hurling. They're all the dubs, up the dubs. So there's lots of dubs going on, which is a bit confusing. All about the D-ubiquitinase enzymes and proteases, all that sort of stuff, and Protax. But really fantastic addition to the series on highlighting organic chemistry across the UK. Some sad news as the meeting was going on. I got an email from Orgnet, and very sad to hear about the passing of Professor Paul Clark at the University of York. To Will, you and your colleagues and students, condolences from everyone here. That is really very sad news indeed, I have to say, and a sad note to finish on. But maybe on a more positive note, again, thank you to all the presenters, and thanks to all who attended. And for your information, in 2024, the countries that have already been lined up per quarter for this highlighting organic chemistry series. So in Q1, it'll be Hungary. In Q2, it will be Austria. Q3, it will be Sweden. And Q4, it will be Catalonia. So watch out for the emails, and please do support this initiative. And this meeting has been recorded and will be put up on YouTube, so you can watch your old presentations if you wish, but others who are not able to attend can likewise watch it at their leisure as well. So goodbye from Dublin. Thank you very much again, Will, and everyone in the UK and all the 7 speakers. Have a nice weekend.
Thanks, Pat. Thanks, Will.
Everyone.